Started as a Bachelor's of Engineering student here and currently holds a position of an honorary professor at this institute. Today he'll talk about cooperative game theory and explainable AI. Please.
Thank you, Aditi. Good morning, everyone. Thanks for coming at 9:30 itself. Thanks to the organizers for providing an opportunity for me here. And thanks to the organizers also for scheduling me ahead of Professor Harvey Moola, because speaking after him would have been a real challenge for me. Now I can say anything and then get away with it. And so this is a talk where I think there will be more questions than answers. This is somewhat, I would say, preliminary work, where I think there are some very interesting research questions in a very contemporary area. Explainable AI is everywhere. As you know, AI is everywhere, and explainability is turning out to be an extremely important topic in the current times. And then, so from that angle, this is a very important topic, and I think there are some exciting research directions on this topic, and there is early evidence. That this area is very, very promising. There are some very nice patterns that are unfolding, and I hope that this talk will give an exposure to some of those. I think Jayanti Sai Pranati was an MTech's project student who did a project in this area, master's project. And then I have Geeta Charan, Rohit Suresh, Priyanka, Manoj Patil, who are all here. So in case I'm not able to answer any question, they will be there to answer those questions. In terms of outline, I'll first say very briefly about explainable AI and feature attribution. Then I will try to say something about SHAP, shapely additive explanations, which has really emerged as a very prominent way of explainability and feature attribution. I will say why it is good, but there are some caveats there. So then we will start looking at other solution concepts in cooperative game theory. I will try to present an experimental investigation after that, and finally some conclusions. So explainable AI provides a very clear, human understandable reasons for how and why AI/ML models make their predictions. So you have a black box model here. It need not be a black box model always. It can be an interpretable model like linear regression or logistic regression or decision trees and so on. So you have an input and then the AI model will come up with a prediction. So what is explainable AI? It will provide post hoc explanation on why the AI/ML model is making a particular prediction, right, for a particular input. Extremely important because it ensures fairness and accountability of AI models. It is also an ethical imperative. It is especially critical for high stakes domains. For example, if you are in healthcare, the predictions have to be absolutely on the dot. There is
in economics and maths at Rice University, Duke University, Virginia Polytechnic Institute, and so on. To his credit, he has been an elected fellow of various academies, including fellow of British Academy, President of Society of Advancement of Economic Theory, and has been recipient of numerous prizes, the recent one of which is the Kalai Prize of the Game Theory Society 2024. With great pleasure, I invite you, Professor Harvey. He'll talk about a course interpretation of common property and tight guarantees thereof.
Thank you very much for the invitation. It's a great pleasure to be here. My first visit in Bangalore. I still have many places, many interesting places to visit in India, but this one has been on my list for some time. Okay. I'm also very happy that the first talk of this day matches so well in the sense I will explain what I want to present now. Because when I see cooperative game theory applied like that, first of all, I'm happy because for all the years that we game theorists have been studying values of cooperative games, we have been sort of frustrated that from the early 1950s to, let's say, 2010, the actual applications we could show up to the layman to justify funds and so forth were very thin. I mean, there were a few, but nothing of, that would match the scale of what we see now because of their utilization in AI. So it's only a pity that Lloyd Shapley himself is no longer there to see that, but at least people who have been practicing the Shapley value and so forth are happy about that. Okay, so that's one thing. The other thing which makes it very, very compatible and complementary with this talk is that cooperative game theory, as was indeed emphasized, and that aspect of cooperative game theory is really about fair division. There is another aspect which is about stability of coalition formation, but that's the aspect where we actually don't have very interesting general results. It's just too difficult. It's the place where game theory becomes a nightmare of complexity. Okay. But in the part where we actually do fair division, what do? We have a problem like the one that was presented here. We have a problem in which we know something that has been produced, some amount of surplus, some output as described, and we don't know how to share it because we don't know how to attribute and parts. This ensembles all the different responsibilities. I mean, we know that it has been a joint effort, but not one in which the efforts were the same. So who deserves what? And of course, these things have been discussed forever, because the rule of proportionality goes back to Aristotle. Then the idea we will just equally divide whatever has been done or in proportion to the effort. That's something which we know forever. But precisely what the Shapley value and all these instruments do is that they go beyond that in situations where it's not possible to apply in any obvious way something like a proportionality rule, an egalitarian rule, or a combination of those. So they go much deeper. They really deepen our understanding of fair division for this type of problems, in which, again, we know what we divide. It's a simple index, transferable, but we have to understand to evaluate responsibility. The type of fair division problem I want now to discuss about is in some sense the polar extreme, the other part, which we have done and continue to do, in fact, more and more interesting work, is the situation where, in fact, we have agents who are definitely, for all important, relevant aspects, equally responsible or equally non-responsible for the data, for the parameter of the situation. In effect, for instance, in the most important example, their preferences. We are here to divide resources. We know what the resources are, but they are a mixture of things about which us, as participants, we have different preferences. But the key point in this approach is that we are entirely responsible and equally responsible for our preferences, and there is nothing to discuss there. It's not because my preferences are different from yours that intrinsically I deserve more or less. We will have to live with that difference. And the problem, of course, that is the key issue there is that this difference in preferences makes it that a very simple equal division of the resources would not do because it would not be efficient. It would not satisfy the minimal basic economic idea that if you divide resources in a way such that there would be another way to divide the same resources and make everyone better off, or at least some better off and the others not worse off, then you should not do the first one. You should do the second one where everyone is better off. So it's this trade-off between fairness and efficiency, which is the difficult question there, which is fundamentally a different question from the one that the Shapley value addresses. And naturally, I mean, there are contexts where the two sort of questions interact, but we are so, we go so slow in the conceptual forest that these problems raise that for now we are studying them separately. So it's really that. I mean, here the version of fair division I look at is common property. What do we do about common property when, well, it's really common, we have the same rights, but we know that it's, if we want to efficiently use those resources, we have to be smart about it because it's not obvious. Now, why are common property problems important? Well, I would argue they are everywhere. I mean, first of all, they start, when you divide toys, a bunch of toys between children, and we know that there is a real issue, efficiency, fairness. It's already a complicated thing. But then it goes on to slightly more serious things like dividing the estate in an inheritance, dividing the assets when a partnership breaks, be it a divorce or a company that breaks up. And then it goes on, to more and more important issue. I mean, how do we divide the mineral resources at the bottom of international waters? That's one issue that, the law of the sea is trying to address, and that is studied regularly and for decades at the United Nations. And, the air we breathe, the moon, and so forth, all of that are common property. We cannot help it. I mean, we are all equally. So there are some really fundamental things there that, of course, we approach slowly here in the way of, conceptual exploration. Okay, so I guess, the paper exists. I mean, the slightly different title, but it is on archive. Okay, so here I will, for those of you who have a little bit of familiarity with the fair division literature, which incidentally is a literature that started in the 1940s by mathematicians, economists, political scientists, but was enormously revived and given a new life at the turn of this century when computer scientists started to put their nose in it. And as we know, these guys are very, very effective, because they are very cooperative. I mean, they make coalitions when writing papers, which are much more effective than ours. Okay, but we're getting there. Okay, so here, okay, bargaining model. That's one contribution of economic theory where we know that that's an issue of fair division. And I just want to bring attention here to the fact that in a bargaining model there is something called the disagreement point. What we can get if we disagree with whatever is proposed. So that's what I will call a guarantee something which is fair ex ante, it is fair that I can retreat to the disagreement point, but it's not in that model, it's not taken as something endogenous, it's something exogenous. I mean, it happens, I come to the bargaining table with you to discuss how much you're going to pay for my good, the good I'm trying to sell you, and if I disagree, I can just keep it and try to meet other buyers. Okay. What I am interested in, and what fair division literature has been doing more, is to bring concept of endogenous sort of disagreement point, but not disagreement point in the physical sense. Endogenous level of welfare that we will force the mechanism to implement. And here, of course, it's not obvious. What's the endogenous disagreement point? The endogenous guarantee when we divide a large bunch of assets which are all in common property. And it doesn't mean anything to say I'm going to split them in pieces. Okay, so that's the theory that we are interested in. Okay. So first let me give some example. Right. So first the context, I already mentioned that, but let's do it quickly. Exploiting resources fairly and efficiently. There will be a type in the, I will come to a general model soon, but I start by some example and some motivation. An agent will be described by a type which will remain for a while as a very abstract thing. But it's all that matters to the fair division problem, all by which the utilization of those resources will be different from one agent to the other. There is a structural symmetry of the problem, so in the sense that they all have the same set of potential types, and they have to be treated symmetrically, so the resources themselves can treat the agents symmetrically. So it's not the case that some of us cannot consume some of these resources because that would make them sick, and that would invalidate the basic symmetry context. Again, I mean, those are simplifying but crucially important ways to see our way through the concept. And the consequence will be a basic fairness action which comes even before the guarantee, the guarantee which I think of as ex ante fair division properties, or even before the exposed properties like no envy. So equal treatment of equal. If you have the same types, we should end up in the same way, in the same share of welfare. Okay. So we'll be working at the ex ante stage. That's one. It's a fact that after all this time on fair division concept, I mean the two main ones that are now recognized as the two general ideas of importance. One is, what can we say ex ante, just viewing, looking at the resources and one individual type. What is it that we can guarantee on the welfare of these agents? It's going to be a level of welfare that only depend on the resources and my own type, and right. So it's going to give a range to my utility from worst case to best case. I mean, here, as you will see from the examples, I'll be concerned by doing sort of setting the limits of individual welfare, both from below and from above, because they are both important. Okay, and trying to make that range as tight as possible so that ex ante fairness, this initial discussion, already solves a lot of our problem, doesn't leave too much to the final discussion where we will have to go from this baseline to the little extra we can get, by now really going to the efficiency frontier. Okay. All right. Okay, so we'll develop a model of endogenous welfare. We'll come to that in a moment. But before we get that, I need to talk about the unanimity test. Can I get the mic so I can move around a bit? Maybe this one, one here. Okay. Okay. Thanks. Thank you. Thanks. Is that good? Okay. All right, unanimity test. So it's not, I mean, you will see it's related to the key results here, but it's something which is well known for those people who do fair division in a kind of systematic way, but less so, even though it's in fact a very common idea. Because we are equally or responsible or not responsible for the fact that our types are different, this difference should affect us in the same way, affect us in terms of welfare, in terms of the benefits we get from the situation, right? So therefore, if the test is this, if I'm dividing, A is dividing with B, a set of resources, just 2, and A is saying, okay, if my type A was also your type, that would be the unanimity profile for type A. Then, because we would, by equal treatment of equal, we would split equally and we would get that much unanimity level for A. And B makes the same argument and computes the unanimity level for B. What would happen if A was in fact of type B? So these two levels together, there is no reason to think that they will form a perfectly efficient, optimal distribution of welfare. They will be, as a vector, they will be either below or above the efficiency frontier. And what the axiom says is, if they are below, then everyone should get at least that unanimity level, and if they are above, everyone should get at most that. Okay? Very simple idea, but which leads in practice almost all the time to some interesting results. So here are a first example. A case where the unanimity will give you a level which is always feasible and therefore can always be improved. That would be the division of a bundle of arrowable commodities, so vector of goods, divisible goods, between any number of agents, and when the preference over the goods are convex. Okay, so forget about the convexity if you are not familiar, but given this, you actually need this kind of assumption to decide that the agent I unanimity utility is whatever agent I consumes when you give to this agent exactly 1/n of all the goods. Okay, so because of convexity, if we all have the same preference, we should divide. It is efficient to divide equally the goods, and it's also fair by equal treatment. It respects equal treatments of equal. Therefore, and this one is of course feasible because it's always feasible to actually split the goods in equal shares. So therefore, the unanimity test here tells me I should get at least this unanimity level. But then take a different problem, which is the provision of a public good. So there is a public good Z. Z is the amount of public good you want to offer, and it costs C of Z to produce Z unit of the public good. And agent I has a utility UIZ. This is how much utility agent I gets from consuming the public good at the level Z. Therefore, the surplus of this economy, which has transferable utility, is the maximum of what you can get when you produce at the level z. You have a total surplus sigma ui of z. You have to subtract the cost z under standard assumption where the costs are convex and the utilities are concave. There is a maximum, which is not infinity or zero, all right? And that's the problem. How do you divide the cost c of z, given those differences? So what's the unanimity utility there? Well, if everybody is like me, and like ui, then what I maximize here is n times uiz minus c of z. And therefore, that's the same as maximizing uiz minus 1 over n c of z. So if we have the unanimity situation, everyone optimizes under the assumption of equal cost shares and proposes, say that would be the level of the public good, which would give me my unanimity utility, given that we split the cost equally. And now it's very easy to check that, in fact, the corresponding vector of unanimity utility is unfeasible. Because if you could do something better by construction, at whatever other level you would think of, your own cost share should be at most 1 over n, because because of the way the unanimity is defined. Therefore, either it's above the frontier or barely or just on the frontier, but now it becomes an upper bound, right? The agent is guaranteed, so it becomes a nice way to bound the utility level of the agent from above. And it is also clear that as far as a possible guarantee, that's the best you can do, namely the smallest, the most tight, the best you can do, because whenever I give you any level of guarantee, you can always say, okay, but wait a minute, if we were all equal, then I would, by equal treatment of equal, I would get my unanimity level. So that's going to be above, because, well, that's going to be at the unanimity level. So, okay. So those are the two examples, and what the model is about is to generalize that and try to understand the mathematics of the creation of these utility levels, where this thing that we can call guarantee. So here is the abstract model, and can you remind me when I'm like 5 minutes before the end, or 5 minutes? Thanks. So there is a domain of type. So there are two simplifications to be able to get some simple and interpretable results in this model. One is that the set of type is of dimension 1. We can hope to do some things there. There are some partial results, but I'm not going to mention them. But it's not so obvious. And the other is that you also have transferable utility. So whatever is produced that we have to distribute can be evaluated in a single numeraire that can be freely transferred. That's certainly simplified, but it's not necessary, of course, to pose the abstract question. Okay, so N is the set of agents, and the resources, what we distribute, in fact, here becomes a simple function, an abstract function, from the set of X with an arrow, meaning a profile of types. X is a vector of which the components are the type x1, xi, xn of my agents, right? So give me the set of types, I'll tell you how much total utility, in fact, or this utility in some model, this utility in some model, it's a cost, but they will think utility, how much utility I have to distribute. And therefore the symmetry property I need to be able to talk about equal rights, otherwise, the rights are not equal in some hard to deal with way. Say W is a symmetric function of the variables. Okay, fully symmetric in all the variables. And then whatever utility you can achieve is the utility profile such that their sum is at most what is available. Okay, so it's a simple, you can think of that if you want as an abstract cooperative game in which instead of your presence in the coalition being 0 and 1, now it's a certain xi, but you really don't need that kind of interpretation. You will see that there are several. When I come to an example, it will be an example with two completely different stories to justify the same mathematical object.
So when W is like a constant, completely independent of the...
Sorry. Where am I? Here. Yes.
So when W is independent, like is a constant, it's independent of the vector x, it's more like a standard fair division problem where you
when W is a constant. Yes. In that case, for this model, the answer is trivial, because then we will simply do equal division. It's fair because it treats everybody equally, even despite the difference in type, but the types are not relevant to what we divide. What this x should be is everything that matters in influencing Wx. So if here it was a constant, there would not be any problem, right? Because of their equal resource. We have a pot of gold and we have equal rights, no problem, okay? So thank you, because that's important.
So I just...
Yes?
So potentially the agents types are changing, right? I mean you're looking at all instances where different agents have different types.
Yes.
So UI should be a function of the type vector also, like for different.
What UI? Sorry. UI here is just a number. Yeah, I should say that. It's just your utility level.
Yeah, but depending on the type vector, it should be different.
That's if I had a specific division rule,
yeah.
It would do exactly that. It would take the profile of type and say, here is the distribution of utility I propose. But I will not go to that level. I will stay before that level. You will see that it will point in the direction of certain rule of this or that type, and that will be precisely the contribution. Is that without having to go to anything specific about the way those vectors of x's transform in vectors of u's, I will discover some things, some ways to shape those functions. Okay? Yes?
I just have a clarification question. This W is defined, you're defining efficiency notion over here, right? You want to maximize W subject to the unanimity.
No. The maximization is already done. So you give me your type, let's say your preference over these goods, and I computed how much total utility, total surplus I can get. So I know that amount, that's Wx. So I have already done the efficiency computation. That's the simplification that the transferable utility gives me. If there was no transferable utility, I would be obliged to describe Wx as a frontier, as a set of utility profile in dimension n, which would be the Pareto frontier and whatever is below. Okay? But W already subsumes, expresses efficient utilization of the resources, whatever they are. And as you will see, the resource sometimes will be a preference, sometimes will be an effort, sometimes will be a time that I choose a location on the line. I mean, a type is something very abstract. And I'm just saying, abstractly, I know how much there is, and that captures a lot of good examples. Right?
The Pareto frontier you look at will be across all the feasible use.
Yes. Here at this level, I can do the entire hyperplane. I mean, but precisely, I will bring some limits. And now here is the next slide is the key concept. Here is the key concept. The so-called endogenous lower and upper guarantees. Those are functions G minus or G plus There are some G minus, some G plus. They have the same domain X, and they have the property that if it is a G minus, a lower guarantee, whenever you give me your type, xi, I can compute the level of utility, G minus of xi, such that that level of utility I can give you, I can assure at least irrespective of the other types by the other n minus 1 agents. So the only thing that G minus function depends on is, of course, the set of type, that's its domain, and the number of other agents, of course, and the knowledge of the function W, right? But the point is here, some people call that the fair share approach. The idea is it's a very useful index if it exists and if it's relatively high, because it means you can delegate the issue of finding your fair share without even knowing what will go on, simply by receiving a message that tells you whenever you will be involved in a division situation, I'll tell you how much you get. If you are satisfied with that, you know that you will not be ripped off below that in whatever negotiation or rule. Okay, so sigma of the G minus xi for any profile should be less than W, and W should be less than sigma of the G plus, for this time for upper bound. And remember, in fact, in applications, in models, in example, the W could be a cost or benefit. So, that's why we need bounds on both sides. And okay, fine. All right. Now, do such guarantee exist? Of course. Just take G minus xi minus infinity or whatever, very, very bad, and G plus very high, that works. The only thing we are interested in are the choice of those two functions which are as tight as possible, such that if I increase the G minus by even a tiny bit, there will be a choice of the other xj which will invalidate the inequality on the left. Or equivalently, if you have a little bit of continuity in the model, which we have, the W function will be continuous, which will imply that the relevant G function are also continuous. So equivalently, this tightness property means for any xi type, if you give me my G minus of xi, I know that for some combination of types of the other, I will have to receive exactly that. Because for some combination of the types of the other, this inequality will be an equality. And when it's an equality, it means that I will get my G minus, the other will get their G minus, but I will not get anything more. So this lower bound is a real lower bound achieved. It's an actual lower bound. And similarly from the G plus, if I give you G plus of xi, now the tightness means that I cannot lower the G function, the G plus function, without breaking the inequality, violating this inequality somewhere. So for some choice of type of the other, that's the key thing to remember. It gives you an indication, but not in terms of what the other do, what the other could be at some profile. Now it turns out that this is a simple, at least a simple statement of a mathematical question, right? Give me a function W, symmetric, over a set which is an interval or a convex compact or something simple, and tell me what is the set of those functions. And in fact, we looked in the literature, we found one reference where someone, it's not important to go in the detail, but there is nothing on that. At least, maybe some mathematician will someday say, hey, there is a whole book on that, but no, it doesn't seem to be the case. Challenging, what guarantees are tight? If you give me the function W, what are the G plus, G minus? So how much time do I have left now? Okay. All right.
You do want some other properties for G, right? Like otherwise, I could just pick a
Six.
single. You do want some other nice properties of
No?
Tightness, you're coming to that.
Tightness.
tightness.
Yeah.
Tightness, that's what I said. I thought, what, I want the thing to be tight.
Okay.
That's all I want to interpret. For instance, you have properties of the sort, if W is continuous, and you are, then G minus G plus being tight must be continuous. If W is Lipschitz in one variable, then those, you have all kinds of properties like that. But a general characterization we have only in some very special case, already interesting. Okay. It turns out that it's very easy to check because of this inequality that the unanimity level I was mentioning, unanimity of xi, it's 1/n of W xi. This is a notation to say all the vector where all coordinates are xi. I discovered that recently. I'm very proud of that notation. I hope it will be adopted because we so often have to write xi. No, do that. Okay. And also you can do xi for k types and xj for n minus k types. I mean, and I use that in the paper all the time. I mean, it's probably something to remember. Okay. So just rewrite this inequality before. Right. Rewrite it when all the xi's are equal. Then you get exactly what I write here, right? Yeah, you put all the equal. So therefore it says, if by chance the unanimity level happens to be itself a lower bound, a feasible lower bound, it's the best one. And if it happens to be an upper bound, it's the best one. And what happens is the case where it would be both an upper bound and a lower bound is equivalent to the fact that W is additively separable, that W of x is sum of the f of xi for the same function f, which is the unanimity up to a scalar. So what you know is that the unanimity, if you can make it a feasible upper or lower bound, you have already solved 1/2 of your problem. But the other half is bound to be difficult. So definition, the function W is super or submodular on the box, LH. LH, remember, is the interval of types from low type to high type. And simply says supermodularity means that when I go from xi to yi bigger than xi, then the difference W of yi minus W of xi is weakly increasing in the other parameter xj. That's for supermodular. I mean, it's a standard definition and nothing, but just it means essentially that the cross derivative dij is non-negative if everything is smooth. But it doesn't imply anything about W being either monotonic or convex or concave. It's a different sort of condition. Even there are some connection, of course. But general result: if W is supermodular, unanimity is the uniquely tight upper guarantee. And on the other side, we have two canonical standalone guarantees, which are therefore lower guarantees, which take the following form. They are depending, of course, only on your parameter xi, but in a way which, in some, as you can see from the formula, measures the distance between what you would do if your xi was L. To look at GL. If my type was L, then this first term would be like here. It would be WL everywhere minus n minus 1 over n WL everywhere. Therefore, it would be 1 over n W ln. It would be my unanimity. So you have this benchmark in your head. That's in some sense the normal thing. And if you deviate from that, I'll guarantee you in the minimum your deviation, which, for instance, for now it has no particular meaning, and GH does the same thing but starting from the other extreme. It turns out that those two are always, if W is supermodular, they are always tight lower guarantees. Moreover, they have a role of extreme elements, brackets. I will skip that, but I will show you on the picture of the example. Do I have 5 minutes for doing that? Okay, so they are really canonical and extreme in this problem in a way that's simply explained here. So here is the example. Probably one of the oldest and simplest problem of fair division you can think of, which is already non-trivial, very non-trivial really. W of x is the max of the xi, with two completely different stories, very different, but both interesting. Story one, we are sharing the surplus from one indivisible good with cash compensation, and type xi is I willingness to pay for the good. This is traditional auction context with one good, the auctioneer, I mean, there is no auctioneer in this model, but we know that it's worth a certain amount of, and we know what's efficient is to give the object to the person who likes it most, and the question is how should you pay the others? Okay? Oh, we can think of auction and so forth, and that will come up. In auction, what do? Well, we give it, and then we say, okay, now you give a common fee to everyone else. And this fee is somewhere between first, second, that will come up, you will see. Story two, xi is not at all representing a preference, it represents a need. The need for a capacity level of a certain public good at the level xi. So for instance, you know, we are sharing the cost of building a road, and I will run on it big trucks, so I need a wide road like this, and you need only a small one. Or we are building an elevator in a building that, you know, from floor 1 to floor 6. So if I'm floor 1, I just need a small elevator, the others need more. So we know that we have to build the whole thing, and the question is how to share the cost. So here the cost and the amount that you need is 1-to-1 for simplicity. So you need a level of the public good which will cost xi to provide. And how do we share this max? And this is a well-known example in the cooperative game literature, Little Child or one. Okay. So uncontroversial. So by the way, this is a submodular function. Okay. So now the unanimity will be a lower bound. It will tell me my lowest level of my share, which in the case of the story one will be a welfare guarantee. But in the case of story two, it will be an upper bound on, it will be a lower bound on my cost, therefore an upper bound on my welfare. So in the story of the good, the unanimity, which is 1/n of xi, of course, we split, it's all equal, it's going to be my minimal share from this good, at least the fair share of my value for the good I should get. And in the other story, I should pay at least the fair share of building the elevator up to my floor. I cannot be subsidized by paying less than that. But beyond that, maybe I'm not going to pay. So that's one side of the inequality where we know the solution. Now, what about the other side? So this whole paper started by solving this example as a curiosum and describing, so what are those two things on the other side? The G0, because here you remember the set of type is from 0 to h, just for simplicity. I mean, it's not a restriction. G0 is simply xi. It's your standalone. Huh? At the level 0, there is nothing to pay. And if you deviate, you pay your deviation, or you get your deviation, whatever it is. So it's your standalone xi. And GH is, well, you can look at it, it's 1/n of the largest type. It's very different things. So what does GH plus says in the story 1? If the efficient surplus is H, they will split it equally, because if I tell you you will not pay more than, you will not get more than 1/n of H when your type is H, and actually there is someone with type H, and then you have to give that to everybody. So it's the classic thing of the auctions, right? If everyone has, at least two people have valuation H, the only good price for the auction is H, and everyone will get that. But in story 2, it's not very exciting. On the other hand, because in story 2, it means at the worst, I may have to pay 1/n of paying until the 6th floor if I am myself only on the 1st floor, which is not, which is a bit extreme, right? Whereas if I said G0, I have Xi, I pay whatever, at most, I pay as if the others were not helping me at all. That much I'm ready to do in case, but don't ask me more, right? I mean, it's okay. And what is there in between? Well, in between, you have a line of function GP indexed by a price between 0 and H. And these are the lines. Okay. So this is really where you see the role of these guarantees. Okay, so you have the blue line. So here you have Xi, that's my type, from 0 to H, and you have 3 agents, n equal 3. Okay? And you have your unanimity line, remember 1/n of Xi, so here it's 1/3 of Xi. That's in fact a 1/3. That's the blue line, and that's the minimum on your share. Then you have these two canonical upper bounds. There is the standalone G0 x equal x, right? And there is the egalitarian 1/3 of H. And so those pairs, what you have to think of here in this picture is the pair of the one green line and the blue line. That would be a problem that would be more adjusted, at least in spirit, to the second story, where you would pay at most your standalone cost, but no more. So if you are, if your thing costs very little, you will not pay more. If you have 0, you pay 0, and you will get at least your unanimity. And the other pair, the other extreme pair, is egalitarian and unanimity. And the things in between, they are simply, you fix a P, you look at this unanimity division of the price P, and you draw the red line from here to here and then here. And as you notice, when P varies from 0 to H, you actually obtain those two pairs, those two green lines, right? So what does it mean? It means that P is a conventional price or a conventional amount of public good that is a reference, maybe market value, maybe some existing level or whatever, and up, if your demand, for instance, if it's a public good, if your demand is less than that, then you should pay at most your fair share of the reference price. And if your demand exceeds that, you may have to pay all the extreme incremental costs beyond that, but no more. And there are similar interpretations in the case of a single good, where essentially you say that if you are auctioning a good, or not auctioning, you are dividing in whatever way the good, and there is a reference price for the good, so if your value for the good is below that reference price, you will not get more, you are not entitled more than 1/n of the share of the value of the good, of the reference value, and beyond that, you may get your extra things. So, my time is up, and just to conclude, Well, we go beyond this example by, let me go quickly to, you see there is quite, okay, take home point. Oops, no, not yet, just 1 second. Okay, so the relation to mechanism design, we use this pair of G minus, G plus as a, a nice way to limit the difficulty of negotiating. So you can think of it as mechanism design 0, where the designer is actually not going to come up with any systematic rule, but he's just going to say, look, I know your types, I know this G minus, G plus. If you come up whatever way to some way that meets that, you come to me, I will implement it. If you don't, if you disagree, anybody can come and say, give me G minus of xi, give me something between G minus xi and G plus of xi, and I will be able to do it, no matter what the others report. So it's a sort of way of mechanism design very hands-off. But of course, another way to implement those things is simply to pick a division rule which satisfies those two bounds, and obviously exists. As soon as it does that, because those bounds are tight, the bounds will be implemented. And then it turns out that the pair of external guarantees that you can choose on the other side of unanimity, and always still looking only at modular functions, supermodular, submodular, is always of infinite size, sometimes much more than single dimensional, even though the set of type is one dimensional. There are examples, families in the paper where you have much larger dimensions. But the choice of one extremal guarantee forces you very clearly towards certain division rule, right? And then we have a full solution for the problem of super or submodular function if you have only two agents. That shows and for a family of rank separable functions generally. So even in the case n equal 2, you realize that the dimensionality of these objects is very, very large, because it amounts to essentially the free choice of a monotonic function between two given starting and ending and starting points. So it's very large. So many open questions and so forth. But my hope is that by the generality of the approach, which is already helping to unify certain views that have been around for a while in the literature, we will get some interesting progress. Thank you, and apologize for the...
One or two questions.
So,
Yes.
Regarding types, originally you said these are ex ante.
Yes, these are given. These are given, and they are the description of all we need about the person. So if it's a problem of dividing goods according to your preferences, they describe your preference. It could be a problem where we divide an output produced according to a function, a production function which is not linear, and then it represents your effort or your demand. It could be, and if you had multi-dimension, it could be more, but it is supposed to capture everything that we need to define to analyze the problem.
So if we know something, for example, if it is interim, then
it is. If you connect that to the more standard, Bayesian game literature, it is the interim thing. It is the interim thing where you happen to know your type. In the traditional interim type, you also have some expectations about the others. Here, you only need the range. And because of the necessary symmetry, in fact, this range is the same for everybody. A priori, because again, theoretically, you would like to have a theory of fair division in which rights are unequal. But we don't know how to model that, because unequal rights is the fuzziest and most evanescent concept that I know of, one of those, because it's so much context dependent, and we actually, some of us in this fair division literature do models where they adjust those concepts with unequal rights, but it's never convincing. It's like putting some coefficient in front of things, and fundamentally my point is that at this stage we know a few things about how to model and normatively select an interpretation of rights, but in the case of what we call unequal rights, even if they are defined by some numbers, we don't have a general theory. So it will come, but yeah. So.
In the interest of time, we'll take more questions over the coffee break.
Thank you. Oh, thank you. Very good. That's great.
The second session of the Econ CS Day. We have two exciting talks lined up for the session. Our first speaker is Professor Arunava Sen, who is currently a professor at the Indian Statistical Institute, Delhi. Professor Sen obtained his PhD from Princeton University in 1987 before joining ISI. His research interests are in game theory, social choice theory, mechanism design, voting, and auctions. Today he is going to talk about stable matching with payoff guarantees. Over to you.
Thank you very much. It's a great pleasure to be back at the Indian Institute of Science. I don't know, it's my fifth or sixth visit, at least, thanks to Professor Nalhari. And I'd particularly like to thank Siddharth for putting together this event, and to the students who have helped put it together. This is, an earlier version of the paper I actually presented in Professor Narhari's retirement conference. So apologies if you've heard it before, but I think this is an improved version of that. At least I understand the paper a little differently from what I did last year. So let's, okay, so this is joint work with my student Vilok at ISI and two Iranian colleagues, Mohsen and Rasul, whom I met on a trip to Iran several years ago. Okay, so so here is the here is the problem. So we revisit the very classical problem called the assignment game, studied in Shapley-Shubik, 1971. So this is a model where firms and workers are matched together and divide a surplus. And this potential surplus is defined for every firm-worker pair. And so we call this the surplus matrix. And so this was the Shapley-Shubik model. So what we are interested in is trying to analyze the case where agents observe, for instance, they don't observe the assignment. They don't know who's working for whom. They don't know how they're splitting their surplus. And as we shall see in this model, we actually don't even know whom you are matched with. Even that will not matter. So they cannot observe, anything other than, for the moment, let's say, who they're matched to, right? And the question is, what matching and surplus division can we expect in this situation? So here is what one might want to do, and I might say, without offending anybody, in a sort of conventional, sort of game theoretic, non-cooperative way, which is to set up some bargaining protocol in which people meet, make proposals, etc., etc. We don't know what the other guy is getting, so we don't know who to bargain with, what offers to make. Then we, don't know what solution concepts to use, and stuff like that. And we know generally, I'm not an expert in this, but the specific nature of bargaining protocols makes a huge difference in what kind of solutions we arrive at. And what we want to do is to completely avoid all that. And what we do, and this, we develop a very simple notion of stability without making any assumptions on bargaining protocols. And it's based on this idea of payoff guarantees, somewhat different from the idea of guarantees that Hervé used, but still guarantees in a, in the standard understanding of that word. And it's the notion of guarantees that each agent can infer from the surplus matrix. So as I think I said in the earlier slide, the surplus matrix is common knowledge. Everybody knows it, everybody knows they know it, etc., etc. So we make no assumptions about this. So supermodularity, payoff discretization, which occurs in certain papers in this literature, we make no such assumptions. And what we do is we characterize stable outcomes, and the predictions are quite robust. And I must say that at some level, this seems surprising to me. I'm sure it's not when you understand it in the proper way. So let's plunge into details, and the way that I will do this talk is that I will basically work through an example, and that example will hopefully make things clear, and then I'll just state the main result. There's some work and notation involved when I set up the notion and so on, but the example hopefully will make everything clear. So finite set of workers and firms indexed by I and J, a number of firms and workers the same for convenience. Match between worker I at firm J generates surplus of Vij. Payoff from the outside option is 0, and an assignment is a function, is a map from I to J. Every worker works for exactly one firm, and and a matching outcome is a pair mu W, where mu is an assignment and W is an I-dimensional wage vector. So the wage vector tells you how the surplus is divided between the matched worker and firm. So again, standard definitions. Efficiency, the assignment mu bar is efficient if it generates the maximum surplus. Okay, that's efficiency. And it's individually rational if every agent receives a payoff of at least 0. The outside option is 0, so if you don't give the guy 0, he'll walk away. Okay. And so here is, we come to the notion of stability, Shapley-Shubik. So the matching outcome mu W is blocked by the worker firm pair Ij if I and J are not matched together, and coming together, they generate, they get less than Vij, right? So Wi is what worker I is getting. Vi prime J minus Wi prime is what firm J is getting in its match with I prime. Together, they get actually less than Vij, so they can obviously do better, strictly better, by coming together and by abandoning their current partners. And the matching outcome mu W is stable if it is individually rational and cannot be blocked by any worker firm pair. Okay, so this is the Shapley-Shubik model, and now we say that how do we talk about stability when you don't know what your what the guy that you want to block with is actually earning, right? So how do we approach this question? So before we do that, let me in 5 minutes run through the Shapley-Shubik model, and sorry, I'm going the wrong way. Oh, what's happening? I just seem to be going the same way, no matter what I do. Okay. I should use that. Okay. I go back. No, this one. Yeah. Okay. So Shapley and Shubik set up this LP problem. We have these variables xij, where xij is 1 if I is matched to j and 0 if it's not. And so we consider the following primal problem: max sum of Vij xij, subject to sum of xij equal to 1 over j and sum of xij equal to 1 over I. Importantly, xij is allowed to be anything in the interval 0, 1, right? Although we know that a matching is one where the xij is either 0 or 1, right? Otherwise, the matching is fractional, and that's not a real matching. So we can write down the dual problems, the dual problem, Wi and Fj are worker I and firm J's payoff. And so this is the dual problem. And okay, so so the maximum value of the LP is attained with all xij equal to 0 or 1, which corresponds to an efficient assignment. Although I start with a problem where I don't constrain the xij's to be 0 or 1, but anything between 0 and 1, there is always an efficient solution with 0 or 1. And the solutions to the dual of the LP problem correspond to the stable wedge vectors. So this is all Shapley-Shubik, and again I'm going the wrong way. Okay.
Professor, so you basically mean that one of the extremal points will always be the solution.
Exactly, integral. Okay, yeah.
All extreme.
Huh?
All extreme points are equal.
All extreme points. In general, I'm interested in the efficient ones. So the wage vectors corresponding to the stable matching outcome form a complete lattice. So that is, if I take W and W prime to be stable wage vectors, then the component-wise maxima and the component-wise minima also define stable wage vectors. So this leads to a worker optimal and a firm optimal wage vectors W upper star and W lower star. Okay, so so this is Shapley-Shubik. Matching outcome mu bar W stable if this is efficient and the wage vector is the solution to the dual of the LP problem, and let mu bar W be an arbitrary stable matching outcomes, a stable matching outcome. Then there exists these wage vectors W upper star and W lower star. Okay, I missed a W lower star here, such that these are the maximal and minimal. These are the best wages for all workers, and the other one for all firms. Okay, so yeah.
Sorry, what is E?
E. Yeah, E is the set of all efficient matchings. Okay, it may not be unique. Actually, this will be a point we shall see. Yeah.
I did not understand the maximality thing. You said in property 2, you said Wi star bigger than Wi, but you don't. It doesn't mean that Wi star is the largest you can get, or is it something you add? I mean, where is the maximality?
So for any W which is stable, for any W which is stable, W star is simultaneously stable for all.
So then it's independent of the W.
No, this is an arbitrary stable matching outcome. This is the one that I get from the yeah. So
shouldn't it be that first there exists W star such that for any mu, for any W?
Yeah. Okay. I'm sorry.
Okay.
There exists W star. It's not with reference to this. Okay. This is
So
absolutely right. It's here. Okay. Absolutely. Yeah.
How are we defining efficiency?
It's just the matching. So suppose there are 2 workers and 2 firms.
Yeah.
So there are 2 matchings. Worker 1 with firm 1, and therefore worker 2 with firm 2, or worker 1 with firm 2 and worker 2 with firm 1. Yeah.
Optimal solutions of the primal LP.
Yeah, the optimal solution is primal layer. Okay, I'm sorry. So there exists such that, yeah. Okay, so here is where we begin, which is the notion of a payoff guarantee for an agent. So an agent proposes a wage or a split to an agent on the other side of the market to block only if it is certain that the other guy will accept. So you make an offer to the other side only if you are certain that it will be accepted, right? So if I know, so suppose I'm getting 10, but I know that I can, there is another guy on the other side of the market who is, with whom I can get 25, and that person is getting no more than 12. Okay, then I can give that person 12 plus epsilon, and I can get more than 10, right? So my payoff guarantee is 13, because that other guy will, I know for a fact that if I give him 12, he will accept. Okay, that's the notion of a payment guarantee, right? It is something that I can, it's an offer that I can make to somebody else, right, which is certain to be accepted.
I mean, independent of each payoff he has in the stable.
Yes. Not stable. I don't know whether it's stable or not. I know that there is that guy there. He has somebody working for him. I don't know how they're splitting, but by making an offer to that person, he's bound to accept. Okay? So we'll see in the example. So this is the payoff guarantee for an agent, and the first assumption is that no agent will accept, irrespective of what bargaining protocol you write down, a payoff less than their payoff guarantee. Okay, and the second assumption is that, but this is common knowledge, that no agent will ever accept anything less than their payoff guarantee. Okay, so I have no idea who others are being matched to. Yeah, I have no idea how much they're making, right? But yeah.
So if I'm correct, at this stage you are giving properties which will, in some sense, if you make the argument, define the guarantee as satisfying those assumptions. You have not defined it yet.
No. I have not defined it. So it's going to be a recursive process.
Okay.
It's going to be a recursive process where these payoff guarantees will be recursively updated. Right? And I'm going to be able to put very tight bounds on what is going to survive this iterative process. So these, as I said, payoff guarantees are computed by iterated elimination of blocked matching outcomes, and we eliminate only those matching outcomes for which is certain that the matching outcome will be blocked. So I'm actually going through, now let's go through this example. Okay, and this is actually the example in Shapley-Shubik 71. Okay, so there are three workers, I1, I2, I3, three firms, J1, J2, J3, and this is the payoff matrix, V. Okay, and there is a unique efficient matching, which is the diagonal, okay, which gives a surplus of 16. Okay, you can check other matchings will give you less than 16. And if you solve the dual, then you will get W lower star 350 and 561. I'm not going to go into it, but let's just keep it for the moment. Okay, so now let's go through this iterative process, right? So initially, so this is all a thought experiment. You know, everybody is sitting and thinking. It's all in their heads. At V, step 0, V is actually the maximal payoff of firms, in the sense that workers do not know, what the firms are making, but they know they can't be making more than those numbers there. So that's the maximum.
The optimal weight vectors need not be unique.
In this case, it is.
In this case, it will. Yeah, isn't it?
Yeah, in general, if there are two ways to do it,
In general.
you could have two ways.
The set of stable weight vectors form a complete lattice.
Yeah.
So there are many optimal.
The many optimal, the minimum and the maximum. That should be unique, right? That is unique. The set of stable vectors is not unique.
That is the set of optimal solutions to dual is not. There are many.
Okay.
Yeah.
Okay. Now let's. Where was it? Yeah. So now suppose that I1 is paired with J2 or J3, right? So just think of this thought experiment that I1 is not matched to her efficient partner, which is J1. In fact, is matched to either J2 or J3. Okay? Now, she has no idea what J1 is being matched either to I2 or I3 because she's not matched to J1. She's not matched to I1, sorry. Now, the maximum that J1 can get, if not matched to I1, is 5. Okay? So, I1 knows that if it makes an offer, by coming together, she can get 8. Right? So by making an offer of 5 plus epsilon, J1 is bound to accept. And therefore I1 can guarantee 3, whether or not matched to J2 or J3. Okay? Oh, I think I again blew it. Okay, yeah, here. Suppose I2 is not J2, J2 is paired with I1. So from V, I2 knows that J2 cannot get more than. Okay, so this is very confusing. So, okay, we started with this and now we are on this. So now what we can do is that we can, revise the maximum that, that I1 can get. And which is that.
You did an argument for I2.
Did I do an argument for I2? I did an argument for I2. Okay, I did an argument for I2. So this is always very confusing, but let's do the argument for I2. Suppose I2 is not paired with J2. Okay, but the argument for I1 does not work because of the argument for I1 does not work because J1 could be matched to I2 and be getting 9, whereas together they can get only 8. Okay, so let us make the argument for I2. I2 who is not matched to her efficient partner J2, so is getting So I2 knows that J2 cannot be getting more than 2 or 0, right? So I2 and J2 can generate 6. So if I2 gets less than 4, she can offer a little more than I2 to J2 and offer that J2 is bound to accept. Okay, so J1 cannot get more than 5 if it is paired with I2, and J3 cannot get more than 3 if it's paired with I2. Okay, why? Because 6 minus 2 is 4. Okay, and therefore J1 cannot get more than, out of 9 cannot get more than 5, and J3 cannot get more than 3 if paired with I2. Okay, and you can check that we cannot do anything for I1 and I3. Okay, so now we can revise this matrix V to this following matrix where I have changed these numbers here. This has now become 5 and this has become 3. Okay, because I know that J1 cannot be getting more than, J1 cannot be getting more than 5. Okay, now let's not, so I was making the argument for this matrix rather than the other one. Now notice that I1 being paired with J2 or J3, right, together can get 8, but J1 can get a maximum of 5. Okay, so it means that the maximum payoff of J1 is 5 if paired with I2. So I1, J1 can get 8. So I1 is guaranteed 3. Okay, so that means that I1 and J2 are together getting 2, but J2 is getting minus 1 because I1 is guaranteed 3. So in fact, this I1 J2 pairing cannot occur. Okay, and also J3 can get a maximum of 2 if paired with I1, right? So we can again revise this matrix to get the matrix
How are you
V2.
revising the matrix? Like, how did you
So these are the maximal amounts that firms can get.
Okay, I see.
right? Initially it was the whole matrix. Now each worker computes a minimum that this worker can get, therefore a maximum that the firm can get. So you revise those.
Always down.
Yes, in this case, always. Yeah, the firm's things are always coming down. It's starting from the maximum and it's coming down.
I mean, first argument was that I2 is sort of an expensive employee. He's always bound to.
So I2 knows that, I2 is not being matched to her efficient partner J2.
But it will always get 4, so you subtract off 4 from that.
So you know that J2 is being matched to somebody who is lousy, so it's getting something really low. Okay, so that gives a guarantee to I2. Okay, once that lowers the guarantee for J1 and J3
In that row.
in that row. But then it leads to another,
Yeah.
because it's all common knowledge. Okay, so now we have this updated revised maximal pay of V2, and now I put a cross against I1 J2 because this match cannot occur, because this would imply J2 getting a payoff of -1, impossible. Okay, so now again go back to I2. Okay, now notice that because J2 has disappeared, right? J2, this number was 2, now the maximum is 0 that J2 could be getting. Okay, so the payoff guarantee of I2 when not paid with J2 must increase by 2. So the maximum that J2 can get when paired with I1 and I3 are now 3 and 1 respectively, right?
Why should it increase by 2?
Because that number was 2 there before, which is now a cross. Yeah, so that number has been ruled out. I know that it is not possible for J2 to have been matched with I1. So J2 must be matched with I3 and is getting 0.
But before I2 had 4 guaranteed. Now he's going to have 6, which makes sense. I mean, I agree. He's guaranteed 6.
No, at most 6, right? But we know that he is not matched with J2. We are looking at cases. So let me jump ahead. We are looking at cases where people are not matched to their efficient partners. And what we are trying to do is we are trying to eliminate as many of those as possible. Okay? So it's a bit confusing, but that's what we are doing. Let's see how far we can go. Okay? So since I2, J2 is now ruled out, J2 must be paired with I3 and can get at most 0. So the payoff guarantee of I2 when not paired with J2 must increase by 2. So the maximum that J2 can get when paired with I1 and I3 are now 3 and 1 respectively. Okay? So now we have a new payoff matrix, this, right? So what we did was we reduced these numbers by 2. Okay. Now we do again the maximum that, okay, so now we've reduced it to 3. Now notice what has happened is, now let's think of I3. Well, I3 not matched to their efficient partner, J3. Now this number has the maximum that J1 can get if not paired with I1 is now 3. Okay, so maybe I need to do this. Since I1, J1 can get 8, I's payoff guarantee is now 5, right? Because this is now 3. So this is incredibly confusing. So since I1, J1 can get 8, I1's payoff guarantee is now 5. So the maximum that J3 can get if paired with I1 is 0. Okay, so if I do it once again, I get this matrix. Right now I have changed this to 0. Where is that? Yeah, where this one here is 0. Now again what I will do is that the maximum that J3 can get when not paired with I3. So now let's look at this guy here, not paired with this one, right? So so J3 must be paired with I2 and is getting only 1 now because that other one was 2 and that 2 has been removed. So the maximum in that column has gone down from 2 to 1. So now there is again an upward revision of the payoff guarantee of I3. Okay, and so I3's payoff guarantee is 1. So J1 can get a maximum of 2 if paired with I3, while J2 can get no more than -1 if paired with I3. So this is also eliminated. So I3 J2 is now ruled out. So the new payoff matrix is V5. And I have eliminated all except those two. And now I will eliminate those as well. J1 gets at most 2 in its pairing with I3. And I1, J1 can get 8. So I's payoff guarantee must at least be 6. Okay? And since I3, J3 gets 5 in the original matrix, J3 must be getting -1. So I3, J3 is also impossible.
So the matrix goes down, but the guarantees can go up.
The guarantees of workers are going up.
They are
Yes, yes, and that's exactly what's happening. The payoffs are going up. So what we are doing is showing that if the pairing is part of an inefficient assignment, it becomes infeasible. They exceed Vij. Okay? So then what we get is this. So which is impossible. So essentially all that is left is the diagonal.
Because now you eliminate the 2.
I eliminate the 2. So I'm afraid for making a bit of a mess of this. One really needs to think clearly while doing it.
Would it work already 2 by 2, or is it too simple?
2 by 2 is too simple. Yeah, 2 by 2 is too simple, but 3 by 3 is the minimum. So you get the diagonal element. Okay? So what does that mean? You get efficiency. Is this general? Is this general? And so this is our theorem. Yes, generically, in the sense that if the efficient assignment is unique.
But you could do it also the other way.
Yeah, but it's enough to do this argument. It suffices to only look at non-efficient pairings and workers matching with their efficient firm partner.
So the other one would give the same result.
You would give the same result because you would. So let me carry on. So nothing but efficiency survives, at least in Shapley-Schubeck. What happens with the efficient one? So think of what's happening with the efficient one. Now I know that people are assigned to their efficient partners, but I don't know what surplus, how they're splitting the surplus. I don't know that. Okay? So what can I say about that? Okay? And so I've written this, and the original matrix with underlining to show that that's the efficient one. So I can now I know what when I want to deviate and block with somebody, I know the maximum they're getting from the efficient match. I've reduced the set of I don't have to look at the maximum here. I just know that guy is getting at most that. so I can run through the same thing, and I'll make a mess if I try to try and work through it. But let me say that the final guarantees for workers are 3, 5, and 0 for I1, I2, and I3, and these are the minimal payoff of workers and coincides with W lower star from Shapley-Shubik.
The 3, 5, and 0 do not appear here. I mean,
Yeah.
you said I2 is guaranteed.
No, this is the maximum that the firms are getting. So this is 8 minus 5 will be 3. Right? Because this is the, these are the maximum that firms are, these are the maximum that firms are getting. So this is what the workers are getting, Bij minus that. And I cannot make any further improvements, using the same logic that I did before. So you get stuck with this iteration. Okay, so this is the minimum amount that that workers can get. So there's the maximal amount that workers there's the maximal amount that workers can get, and it's therefore the minimal amount that a worker can get, and that's 3, 5, and 0, and it coincides with W lower star. Okay, and if I do it for firms, then, and again, then those will give you the maximum that workers can get, and that's 5, 6, and 1, and that coincides with W upper star. Okay, so what we've seen in the Shapley-Shubik example is that if you say that nobody accepts anything less than their guarantees, correct, then the only pairings that survive are the efficient ones, and the minimum and the maximum are given by W lower star and W upper star. Okay, and so if you want to look at a diagram, yeah.
So in the example, your guarantees do not actually
No.
to the same.
No, so that's the one that, as we said, that's left on the table for them to negotiate, right? So the picture from the right-hand side, this fuzzy-looking picture is actually directly taken from the Shapley-Shubik paper. So it's sort of a ramp-like thing because it has this lattice structure, the maxima and minima are this thing, and this is what we get. So this is the smallest cube that is described by this point and that point. Okay. So here is so this is the slightly tedious part. How much time do I have? 2 minutes. Okay. So here, we look at the, we formally define what a stable payoff guarantee set is. So it is a structure which consists of a set of assignments and payoff guarantee for workers, minimal and maximal for every mu in capital mu, yeah, I'm not going to be able to describe this. So we have so we have this notion of guarantee consistency. If the maximum is actually greater than equal to the minimum, otherwise that matching is not feasible. Okay, and so then we define the stable payoff guarantee set recursively, right? It's reminiscent of Bernheim-Pierce rationalizability and indeed Hervé's work on dominance solvable games, in which you iteratively eliminate weakly dominated strategies. So this is not weakly dominated strategies, but matching outcomes which can be blocked, right? We eliminate those, and then This is defined by the infinite intersection. And so let me just, existence, every stable matching outcomes belongs to the SPG set. So if you look at an output of Shapley-Shubik, that will never get eliminated. In particular, you will never be able to eliminate the thing which is efficient. Everything else will lead to chaos, but this will not. So every stable matching outcome belongs to the, I even had a proof which is very simple, but I don't have time. So here is the theorem. Assume that V admits a unique efficient assignment mu bar. The SPG set gamma star is the set mu star equals a unique efficient assignment mu bar. And with the payoff intervals being defined by W lower star mu and W upper star mu. And the convergence, unlike many of these games, is finite. A finite number of steps, we have an upper bound.
And the numbers are rationally if you start with.
Sorry?
Those numbers W star, W upper star, they are rational, I suppose. If you start from integer or rational numbers, you don't go to non-rational.
So W star, lower star and W upper star as in Shapley-Shubik,
Yeah.
and they will be integers if the numbers are
Yeah, so if you start with integer,
W star, and they are the original best.
yeah. In the Shapley-Shubik, so if you give me the Shapley-Shubik model, I will tell you what W lower star and W upper star are from that model. And so relaxing the assumption of unique efficient assignment. So what happens if the efficient assignment is not unique? We have an example to show that if you have just two efficient assignments, not one, but just two, then every assignment can occur in the set U star, right? So that efficiency being unique is incredibly important. But it's generic, right? Generically, it will be unique, right? If it's not unique, you perturb something slightly and it will become unique. So it's not a major assumption. What happens if the assignment is actually observable? You can see who's going to work with whom. In that case, the same, you don't need the uniqueness assumption. You don't need the genericity assignment. So just one last sort of concluding thought. The weird thing about this analysis is that you don't even need to see who your partner is. You can just sit and think, and you can figure out that you must be matched to your efficient partner, right? If you right, nothing else is actually consistent with payoff guarantees, common knowledge of payoff guarantees, and the common knowledge of V. These are the three ingredients which drive it, and the proof consists of showing that at every stage of the iteration, there exists some inefficiently matched pair who will improve, the worker will improve their payoff guarantee. Strictly improve. Right? Number one. This will mean that after some point, everything inefficient will be wiped out, as we saw there. The second thing is that the efficient one will never be wiped out. That's very easy to show. And the third one, which takes some work, is that then this converges to this W lower star, W upper star. So, yeah. So it seems that, the complexity of bargaining, if you will, should rests on this fact that I only know the VIJs for the firms, for my firms. I don't know the VIJs for others, right? So I may know what I'm getting when matched with particular firms, but I have no idea what other people are getting when matched to various people. That may be one way to resolve this. Otherwise, efficiency and so on falls out without any assumption on supermodularity or anything. Just this very basic idea of a payoff guarantee and the common knowledge of payoff guarantees. Okay. Thanks for not mentioning them.
Maybe we'll take one quick question.
Yeah.
Is there a bound on the number of iterations for convergence?
Yes, yes. It depends on the matrix V. We actually have a number for it. It isn't particularly informative, but it depends on the structure of V, and I can tell you what it is, an upper bound. Yeah.
Have a small token.
Thank you. Thank you.
Okay. So our next speaker is going to be Debashish Mishra, who is also a professor at the Indian Statistical Institute, Delhi. Professor Mishra obtained his PhD from the University of Wisconsin-Madison in 2004. Following this, he was a postdoctoral fellow at the Center for Operations Research and Econometrics at UCL, Belgium, before joining ISI Delhi. His research interests include the theory of auctions and mechanism design, social choice theory, and game theory. And today he is going to talk about transferring teachers across schools. Over to you.
Hello. Okay, thank you everyone for staying. So how long do I have? If I can.
40 minutes.
40 minutes, so 1:05. Okay. So I'll try to finish by 1. So thank you Siddharth and others for organizing this event. It's a great conference, especially around Urway, and it looks like all the talks are related to fairness in some way or the other, so it's very nice. And so this is a paper that I have presented earlier to some of you are aware of it. So apologies for that, but no harm in listening to the same paper twice. So this is joint with so Mendu, Arunav, Jay and Sonal were spread across 3 continents. So economists are also collaborating on large scale. You can see that now. Okay, so it's a theoretical paper, but it's motivated by something which happens in India, and it's a kind of a real problem. So most of you may know that the Right to Education Act was implemented by Government of India in 2009. The mandate was to improve the student-teacher ratios in schools. So in particular, the Right to Education Act specifies essentially how the governments can do these kinds of adjustments to student-teacher ratios. So this is a quote from the Act itself. It says that the central government, appropriate government, or local authority, as the case may be, shall redeploy teachers of schools having strength in excess of the sanctioned strength. Okay, so as many of you know also that education can be both a central subject as well as a state subject, and depending on which government is operating the schools, they would have these periodic transfers of teachers to balance this imbalance of student-teacher ratios. Okay, so there have been some empirical studies about how the government should be doing these transfers and what are the effects of correcting these imbalances and so on and so forth. So this is a study which was done in 2018, and to quote them, they say that the transfer of teachers to correct imbalance in the distribution of teachers is technically referred to as rationalization. In principle, teachers can also be transferred for other reasons, but the kind of transfers that the literature talks about, or we are talking about, or the Act talks about, is about correcting the imbalance of student-teacher ratios. Okay, so this paper actually has a data set of about 9,000 schools in the state of Haryana, and what they do is they classify the schools as surplus schools or deficit schools. We know what it means in the sense of having excess teachers or deficit number of teachers, and then they consider the process of rationalization which was done by the governments. So the formal model would be that there is a set of surplus schools, let's call them S, and there's a set of deficit schools, let's call them D, and the Act specifies that the teachers in the surplus schools need to be transferred to deficit schools. So that's the mandate of the Act. So the set of teachers in surplus schools is denoted by T, and these are the only teachers that need to be transferred. So as I said, in principle other teachers may be getting transferred, but those may be for other reasons. For correcting the imbalance, the Act specifies that the teachers in the surplus schools need to be transferred to deficit schools. Each teacher TI obviously belongs to a unique surplus school, call it O of TI, where it is currently teaching. So there are a couple of notations that we need to keep track of. Each surplus school Sj has a surplus number alpha j, which is a positive integer. This is the maximum number of teachers that surplus school can transfer. Okay. So that's also a provision in the Act that you can't make a surplus school a deficit school by process of this transfer. So the surplus number alpha j is actually an upper bound on the number of teachers you can transfer. Similarly, a deficit school dk has a deficit number beta k, and that's the maximum number of teachers that can be transferred to this deficit school. So what does a transfer achieve? Transfer basically provides a certain number of new teachers, call them Fk. Fk is the number of teachers which gets transferred to a deficit school dk. And as a result, you get this new deficit number beta k minus Fk, where beta k was the original deficit number of school dk. So our objective in this paper is to find a transfer F that equalizes across all deficit schools the post-transfer deficits. That is, this vector beta k Fk across all the deficit schools are equalized as much as possible. Okay? So the takeaway from the talk will be that there is a unique way to do this, and I'm going to give you an algorithm which will achieve this equalization.
So far, this is a flow problem.
This is a pure problem here.
Flow.
It is. In fact, I'll set it up as a flow problem. Yeah.
So yeah, my question was the teachers are interchangeable.
Teachers are.
I mean, we're not like okay, only teachers of X type can be moved.
So there are no X types, but notice that each teacher is already in a surplus school, and different surplus schools have different constraints in the number of teachers that they can release. So there is some heterogeneity across teachers in the sense where they are employed currently.
But that's with the school. There's no properties.
So I will say that teachers will also have some restrictions on which deficit schools they can go to. Okay, so
But we are not looking at the specialization as in the subjects.
I will come to that. Our results will extend to even if you have subject teachers and so on. So
It got you.
yeah. Okay. So here is a map from the Haryana, from that same empirical paper. So if you look at Haryana, if you look at those data set that they have, the blue dots actually correspond to the surplus schools and the red dots correspond to the deficit schools, which is as of I think this is a map from 2013-14, and basically it shows that there is certain areas which have a lot of surplus schools, potentially the urban areas, and the rural areas has a lot of deficit schools, and this is after one round of transfer that has happened in 2011-12, right? So they do this transfer every 3 years. So this one of the transfers was done in 2011-12, and you see there is a decrease in the number of deficit schools according to the data, but it's still not there. But anyway, I mean, it's not clear that what kind of policies the Haryana government was following and what is their actual objective, but our objective is slightly more nuanced in the sense that we want to equalize these deficits as much as possible. Okay, so here is the point that I was saying, that teachers are not really homogeneous in this sense. Each teacher TI has an acceptable set of deficit schools, A of TI, that they can go to. Okay, so the planner may put constraints on the nature of these acceptable sets. So these might be mandated by the system itself. So for instance, schools might be divided into zones, urban, rural, or some distance-based measures, and depending on which surplus school you are at currently, you might be prohibited to going to certain deficit schools, for instance. So these might be some exogenous constraints given by the system. This may also be you can think of A of Ti as a preference of the teacher to go to certain deficit schools. And so if you, the preference story would be that these are dichotomous preferences, in the sense that each teacher is indifferent between going to any of the acceptable schools, then staying in its current surplus school, and then going to any of the unacceptable deficit schools. So it's a trichotomous, if you will, preference. So there's a lot of literature in economics, including Irway's work on this, which kind of emphasize that with these kind of dichotomous preferences, you can do nice things. And so this is one observation, and the other thing is like these A of Ti can just be simply some compatibility constraints, right? So as I have already said. Okay, so what's a transfer? A transfer is a map from the set of teachers to set of deficit or surplus schools, satisfying three constraints. The first constraint is transfer has to be of every teacher has to be one of the acceptable schools, acceptable deficit schools, or this teacher should stay in its current surplus school. Okay. Second is surplus schools should not turn into deficit schools. Third is deficit schools should not turn into surplus schools. So these are the three constraints on the transfer. And so now I'm going to formalize the notion of equalization of these deficits. Okay. So what is the notion in which I will try to equalize the deficit? Well, for that I need to introduce some notation. So every transfer sigma generates a post-transfer deficit vector beta sigma. So that's exactly the original deficit minus the number of teachers you get because of transfer sigma. So that's your beta of sigma. And now I'm going to compare two different transfers based on these post-transfer deficit vectors. So I need a measure of comparing two vectors of let's say dimension L, where L is the number of deficit schools. So the way I do it is using this notion of Lorentz dominance. So let me be slightly formal for that. So let gamma be an arbitrary vector in RL and order them from the highest to the lowest like this, and take any pair of vectors gamma and gamma dash, and we say that gamma Lorentz dominate gamma dash if the highest in gamma is lower than the highest in gamma dash, the sum of highest 2 in gamma is lower than the sum of highest 2 in gamma dash, and so on and so forth. Okay. So so those of you who are familiar with majorization theory, this is basically saying that gamma is weakly majorized by gamma dash. Okay. So what we are interested in is a transfer sigma star which produces a post-transfer deficit vector beta sigma star that Lorentz dominates every beta sigma that you can get. Okay. So couple of observations. Okay, so there is a rich theory in majorization about justifying this notion, and I think Hardy, Littlewood, Polya were the first ones to kind of formally define them. And in fact, they have this beautiful result which says that if sigma star is Lorentz dominant, then you can say that if for every other transfer sigma and every continuous increasing and convex function g, the cumulative sum, the sum of g beta k sigma star is less than equal to the same sum g beta sigma k. So you can interpret g as some kind of a cost of these deficits, and so this is kind of saying that if you have a planar with a particular objective function which is encoded in that g, as long as that g is increasing, continuous and convex, this kind of objective is reconciled by this planar, planar's objective.
Like saying you want a flow network with something like Megiddo.
Right, I'm going to come to Megiddo. It's good that you mentioned. So Lorentz dominance is a partial order.
Is this objective, like of finding a vector which Lorentz dominates every other one? Is this equivalent to finding a vector which is close in, let's say, the uniform vector in, let's say, L1 norm or something? Can we say that?
If the uniform was feasible, then that it would be a natural candidate, but uniform is often not feasible.
Like if we minimize the L1 distance from the uniform.
No, that would not generally do it. Yeah, I'll tell you how to get to it. I'll tell you how to get to it. The famous procedures too. So Lorentz dominance is a partial order. Okay, so it's not even clear that a Lorentz dominant point may exist. Okay, but for many continuous problems in economics, it does. So there's a bunch of papers in economics which explores this. But our point is here slightly more subtle than that. We are only interested in Lorentz domination of integer vectors, right? Because the transfers produce deficits which are integer numbers. So we are only comparing integer deficits to integer deficits, okay? So it's not even more, mysterious why such a vector will exist. Okay. And so the main theorem is that it does exist. So a Lorentz dominant transfer exists, and essentially I'll give you an algorithm to get to it. So usually these kind of algorithms are defined for continuous problems, but it poses a lot of technical challenge when you only deal with this integrality constraint. Okay, and that's the main takeaway of the paper, that even with these integrality constraints you can still do it. Okay, so let me describe the procedure. So that would be the first part. So already people are anticipating that it's a flow problem, and it is a flow problem. So I'll set up the network, and so the network is basically a 3-layered network, and the layers are, of course there is a source node which is only for convenience, but the 3 layers are here. Okay, so first layer is basically the set of surplus schools. So you put a vertex for every surplus school, and you put a vertex for every teacher, which are assigned already to a unique surplus school. Then there is a layer of deficit schools. Okay, so these are the 3 layers, and the edges basically flow from left to right. Okay, so the source node is connected to all the surplus school directed edges, and so they have a capacity of alpha j, which is the maximum flow you can push through a surplus school, because that's the constraint. Okay, and then there are directed edges from every surplus school to the teachers it owns, and they have a capacity of 1. Okay, then there are directed edges from every teacher to every deficit school which is in the acceptable set. So only you can transfer a teacher to a school if it is acceptable, and so you put edges for every DK and every acceptable school. Every teacher and every acceptable school of that teacher with a capacity of 1. And finally, all the nodes have sufficiently high capacities except the deficit schools, whose vertices have a capacity equal to their deficit number. Okay, so they have a capacity of beta k, so you can't push more than beta k into these vertices. Okay, that's basically the network. And so here is an example. There are 3 deficit schools, 3 teachers, and these 3 teachers are working in 2 surplus schools. Surplus school 1 has a surplus of 1, but surplus 2 school also has surplus of 1, but surplus school 2 has 2 teachers to transfer. Okay, and these teachers in turn have different kinds of acceptable sets, and so this is the network flow that you can imagine. And basically a transfer is an integer flow in this particular network. Okay, so obviously we know that a maximum flow is an integral flow, so that's a valid transfer. And so what we are interested in is a transfer, integer transfer or an integer flow, which Lorentz dominates every other integer flow in this network. Okay. Okay, so a flow is a map from the set of edges to real numbers, which satisfies 2 constraints: flow balancing and capacity constraints. Yeah.
So in this, how are we ensuring that the deficit schools doesn't become a surplus school?
By the capacity constraints on the vertices corresponding to deficit schools. So any flow would have to respect the capacities of the vertices also. So if you put capacity constraints on the deficit schools, then it won't exceed that. Okay, so integer flows correspond to transfers, and so this slide basically says that our problem doesn't reduce to one of the standard matching problems, because these surplus constraints and deficit constraints kind of play an important role, and they are kind of crucial for all the machinery that we use. And so this example is kind of highlighting that. So let me skip this in the interest of time. So one of the main tools that we use is from a very famous and I think written way ahead of its time paper by Megiddo in 1974. So Megiddo has this beautiful result which is, I mean, it's unfortunate I came to know only recently, that you can basically, to work on these kind of network flow problems, you only need to care about the flows into the sync nodes, which are the deficit school nodes here. So you can ask a question, for instance, if I give you a flow, you can look at the flows into the sync nodes, and these are, you know what the sync node flows are. But suppose I give you arbitrary numbers on these sync nodes and tell you whether there actually exists a flow which can generate those sync node numbers that I gave you. Okay, so that's what I'm referring to as a reduced form approach. The reduced form approach basically allows you to abstract away from the network structure and so on, and just focus on the flows into the deficit schools. Okay, so Megiddo gives necessary and sufficient conditions on these numbers such that there exists a flow which can generate those numbers. Okay, and so to define the Megiddo result, I need to have some notation. So let's say I look at an arbitrary subset of deficit schools B, and I look at maximizing the flows into those B set of schools, okay, deficit schools. So call that B maximum flow, and let's say V of B is the maximum flow you can push into the set of B deficit schools. Okay, by the standard theorems, we know that there exists an integer B maximum flow, and hence V of B is a non-negative integer for every B subset equal to D. Okay, so for every subset of deficit schools, I can define this integer number V of B, which is kind of the maximum number of teachers I can transfer to these schools. So given this, I can define a cooperative game, okay, which Professor Narahari in the morning has already defined. That is, for every subset of deficit school, I can define the largest, or I should say the smallest deficit that I can reduce that coalition of schools to. Okay, so remember the original deficit is beta of B, that's just the sum of deficits of these B schools, minus the maximum flow that I can push to it. Okay, so that defines my W function. So it's a characteristic function where the set of players are the set of deficit schools, and W defines the characteristic function. Okay, so DW defines a cooperative game, and so if I take a vector H1 to HL, so these are the deficit numbers for the deficit schools. I say that they are achievable meaning that there exists a flow in the original graph, or alternatively there is a transfer such that I can get this vector as a resulting post-transfer deficit. So H of k will be beta k minus f of dk. If H is an integral vector, it exactly corresponds to an achievable transfer for us, or an achievable integral flow in the network. And so here is Megiddo's theorem. Okay, Megiddo says that the vector H is achievable, that is, there exists a flow which can generate it if and only if H of B is greater than or equal to W of B for all subsets B of D. Okay, further, W is what is called a convex function or a supermodular function, and integer valued. That is, it satisfies this increasing marginal contribution property. And so note here, of course, that the core constraint for the grand coalition is not binding. So it's not required that H of D has to be equal to W of D. Okay, you can have suboptimal transfers also. But so these constraints appear in many other disciplines of economic theory also, and those of you who have seen this, you can see that it's readily applied in many settings. And so what Megiddo shows, Megiddo and there's a follow-up work by Datta and Ray, they show that there exists an achievable vector that Lorentz dominates every other achievable vector. Okay, and the proof is constructive via an algorithm, appears first in Megiddo and then in Datta Ray independently. And Megiddo only shows lexicographic optimality, which is slightly weaker than Lorentz domination. For these network flow games, Datta Ray is much more general. It shows it for arbitrary convex game that you can construct. They show that there is a particular point which Lorentz dominates every other point in the core of that convex game. So I forgot to highlight that these constraints are exactly like the core constraints that you might have seen in co-predicting. Okay, so that's why there is a connection to core of convex games and the achievability in the sense of Megiddo. Okay, so the main issue is this algorithm output is not integral. Okay, so even though the output of the algorithm or Datta Ray or Megiddo gives a point in that core which Lorentz dominates every other point, it does not give a transfer. Okay. Yeah.
So for the sync nodes, we are defining the deficit scope, right? Shouldn't we also have another sync node where each deficit scope will have an edge with the capacity of how much deficit they will have?
So that's not required. If you put the capacity constraints on the vertices of the sync nodes, that should take care of it. So I don't need to define another super sync node and connect it and have capacity equal to the deficit. That's not required. I mean, if you want, you can do it, but it will achieve the same thing. It will achieve the same.
But the teacher to deficit node has a capacity of 1.
Yes.
So
Yeah. Yeah.
having the constraint of deficit must be
By putting constraint on the capacity of the vertices. Okay. So what I'm going to do is in next 5 minutes I'll describe the algorithm which will give you how to get to a non-integral achievable vector that Lorentz dominates every other achievable vector, and then I'll tell you how we go about going to an integral one from there. Alright, so this is kind of an instructive algorithm. Maybe it has applications in other areas that Professor Narahari was talking about. It defines a solution concept for cooperative games, and this solution for convex games lies in the core and is the most equitable one. Okay. So how does it go? So basically, the algorithm inductively partitions the set of deficit schools into these sets D1 to dk star. Okay. So how is this partition coming about? Well, it's in round 1 you define D1 as the set having the highest average worth. So you choose D1 as the subset of deficit schools such that W of B divided by the size of B is maximized. So you choose the coalition having the highest average worth. Okay, so that's your D1, and give everyone in D1 a deficit number equal to that average. Okay, so equally divide W of D1 amongst the members of D1.
What is K star?
K star is the number of partitions I will create. Okay, I'll create D1, D2, and it will stop at some K star, DK star.
So this is D1 is unique courtesy super.
No, it is not. It won't be unique generally, but you can pick any D1 you like. Break ties arbitrarily. Okay. Okay. So having defined D1 to DK, now how do we define DK plus 1? Well, DK plus 1, because I have already collected D1 to DK, so so suppose dk bar is the union of d1 to dk. So I want to collect a coalition dk plus 1 which maximizes the average marginal contribution to dk bar. Okay, so you look at an arbitrary coalition B, add it to dk bar, and look at its marginal contribution to dk bar, and average it out by the size of B. Okay, and you choose the coalition which has the highest average marginal contribution to dk bar. That's your dk plus 1, and again everyone inside, sorry there's a typo here, everyone inside dk plus 1 gets this particular average marginal contribution. Okay, and so because d is finite, this process will complete and it will generate this d1 to dk star, and it will produce this h star vector where the subsets d1 you get the same h, the subset d2 you get a different h, and so on and so forth. Okay, this will not be integral because I am averaging out. Okay, so it will be fractional, and what Megiddo and Datta and Ray show that H star would Lorentz dominate every other point which satisfies those core constraints. The issue is, can we get to an integral transfer vector by just rounding it? Okay, so just arbitrarily round them so that we get another feasible transfer vector.
So this is computationally hard.
This is not computationally hard. There has been a lot of work after Megiddo's paper which shows that this can be computed in polynomial time. Okay, so even though for general convex game it is computationally hard, for the network flow games that we are considering, it is not computationally hard. Yeah, that's a good question. Yeah. So here is an example just to highlight that arbitrary rounding is not going to work. Okay, so in this example there are 7 deficit schools and 5 teachers who are employed in 3 surplus schools. You do the calculations, you realize that in the first step D1, the schools D1 to D5 will be included, and they will have an average worth of 22 by 5. So that's the deficit number that they will be assigned, and then D6 and D7, the second coalition of schools, will get a deficit of 4. So that's the corresponding deficit numbers that you will get at the end of Megiddo-Datta-Ray algorithm. So now let's try to arbitrarily round it. Okay. So arbitrary rounding means, what do I mean by arbitrary rounding in the first place? So what I will do is I will try to keep the total deficit in D1 to 22. So remember W of D1 is 22. So I'll round this 4.4 vectors such that the total sum remains 22 and every component is either 5 or 4. Okay. So how do you do it? Let's say I assign the first two 5 and the last 3 4. So that gives me 22 and it's an integer. And at 6 and at 7 I don't touch because it's already integer. Okay. So this is a valid rounding in some sense, and I'll formalize it. But essentially what it says is like everything lies in the floor and ceiling of the original one, and wherever the core constraints were binding, it is also binding by my rounding. Okay. So remember the D1, if you add the h, it exactly coincides with W of D1. Okay. And similarly for D2. And so essentially the binding constraints are met by this rounding. The problem is this is not a valid rounding. Okay. Why is that? Because if you look at the coalition of 3, 4 and 5, there are only 2 teachers who want to go to D3, D4, D5. So you can never reduce their total deficit by more than 2. Okay. Their total deficit, every school has a deficit of 5. So their total deficit is 15. So maximum I can reduce is 2. So that maximum, the best I can do for these 3 schools is 13. Okay. But this is putting their deficits to 12, which is not feasible. Okay. So the achievability constraint for 3, 4, 5 is violated. So I need to be careful in doing this rounding so that the core constraints are also satisfied. Okay. So that's a bit tricky. So that's what we will show, that it is possible to do that. Okay. So in the next 5 minutes, That's what I'm going to do. So I'm going to define what exactly I mean by a valid rounding here. So a deficit vector H is MDR consistent if it is an integral achievable deficit vector. So the rounding that I get has to be an integer, and it has to be achievable in the sense that it should satisfy all the core constraints, the Megiddo constraints. Further, it's a rounding in the sense that it is either the floor or ceiling of the Megiddo-Dattare algorithm output, and wherever the Megiddo-Dattare output was satisfying the core constraints in binding with equality, you continue to satisfy them with equality. In particular, the Megiddo-Dattare will satisfy the core constraints with equality at exactly D1 upper bar, D2 upper bar, and so on and so forth. So your rounding must satisfy this. So this is my notion of a valid rounding or MDR consistent rounding. Okay?
Previous one was not valid, why?
Because it was not satisfying the achievability part. Okay, it was satisfying these constraints obviously, but it was not satisfying the core part. Yeah. So the crux of the paper is basically there exists an MDR consistent deficit vector. So it is possible to round it in this way. Okay, and this is also achieved by a network flow approach. In this, so let me not go into these details, but give an example. Basically, we take the original network and add one more layer to it, and this layer is exactly the subsets that I generate, the D1 to D2 to dk star. So I put one vertex for each of them and join these deficit schools to these D1 to dk depending on where they fall. Okay, and the capacities are exactly between, so let me be more precise, between beta I h star I lower bar and beta I h star I ceiling and floor. Okay, so basically the residual that you get from the original deficits after transferring the Megiddo-Dattare amounts. Okay, but between the floor and the ceiling. Okay, so beauty of this is like everything is integral in this network. So if you run a max flow on this, you get an integer solution, and what we show is basically that integer solution is MDR consistent. So it will satisfy those constraints that were bothering us, the core constraints, as well as these binding constraints would continue to be satisfied. Okay, so that's basically the thing. And then the next step is also very general and interesting, that this MDR consistent deficit vector would Lorentz dominate every other integral achievable deficit vector. So remember, this is not a corollary of already Megiddo-Dattare because of the following. Because Dattare and Megiddo show that the output of their algorithm Lorentz dominates every other point. Okay. Obviously, we have gone away from that point. We now have a rounding of that point. It's a great rounding. But now this is obviously not going to dominate every other point in the thing, because we know that Megiddo-Dattare does that. But here we are saying that, okay, even then, this is going to Lorentz dominate every other integer point in the core. That's what we are saying. Okay. So, of course, how I come up with this MDR consistent deficit vector, that I showed you in the last slide. But this proof is actually of independent interest because it does not say how, it does not depend on how you come up with that MDR deficit vector. Okay, so as long as it's an MDR consistent deficit vector, this proposition is going to hold. Okay. So yeah, so that's basically the entire proof. So we have reached a MDR consistent deficit vector, and that's going to Lorentz dominate it. From that, you can backtrack the transfers that you need to get to it, essentially.
But it does inherit this major Lorentz domination because it's a rounding of the...
It's not so clear. Of course, it uses that,
yeah,
but it's not clear that it will continue to Lorentz dominate the integer points.
Yes, yes.
It will not Lorentz dominate the other points,
Yeah,
but it will Lorentz dominate the integer points. Yeah. Wait, so I'm going to conclude with this slide. So what I found fascinating about working on this paper is that at the heart of the paper is one simple observation essentially. Of course, we have to use it in a very complicated scale, but here is something that if you want to take away from this talk, this is what you should take away. Okay, so Hardy-Littlewood polyad. So they show that if I give you an arbitrary number 22, let's say, and I give you, I ask you to construct 4-dimensional vectors out of it. Okay, so they say that if you do the average of 22, that is 5.5, 5.5, 5.5, that average will Lorentz dominate every other vector that you can come up with, which adds up to 22. Okay, so that is something that you can do as an exercise. So average will always be more equitable than everything else essentially in the Lorentz domination sense. So here basically our proof essentially relies on this simple observation that if you do the rounding, okay, of 5.5, 5.5, so the sum remains 22. So you get 6, 6 and 5, 5. Okay. Now I told you that you can't do this rounding arbitrarily, so that's one concern we have already. We have to be careful where we put the 6s and where we put the 5s. But what is interesting is that this 6, 6, 5, 5 will Lorentz dominate every other integer vector which adds up to 22. Okay. So if you will, this is kind of an integral version of Hardy-Littlewood polyad, but this is kind of a very simple observation which you essentially is the core engine which is driving all the proofs. The second point is like where to put the 6s and where to put the 5s, because there are inherent core constraints in the problem. This can't be arbitrary, and so we have to be careful about that. Okay, so these are the only two issues in this. Okay, so extensions. We said that we will only transfer teachers employed in surplus schools to deficit schools, but we can actually do better by transferring some of these teachers to other surplus schools and then rerouting them to deficit schools, right? Because some of these surplus schools might have constraints about, the alpha numbers might be too low, and so it might be better to send them there and then transfer them. So we can accommodate that also. You have to just modify the network, and so there is also one more extension which is possible. Like you can define a type for each of the teacher, which is let's say the subject expertise, and essentially you can do a similar analysis with respect to different subjects and the deficits that you incur in each of the subjects. So you can define a similar notion of Lorentz dominance and rule. So the results also extend to these kind of type models of features and so on.
Will that require having a separate network flow graph?
No, it's in the same network. I just replicate basically, well, in the same network, I basically have another layer of types and types mapping to teachers and so on. You can also establish some incentive properties. If I think of A of Ti as the preference of the teachers, so that's their type. So suppose teachers report their A of Ti's to me, and I execute this algorithm and make this transfer according to this Lorentz dominance deficit vector, then that mechanism will be strategy proof for teachers. So teachers will have no incentive to manipulate. Requires some careful type breaking, but as long as you're doing this type breaking carefully, it will be incentive compatible in a dominant strategy sense. Yeah, so that's it. So there's a lot of literature on Lorentz dominance in economics, and there are also literature on matching with constraints and teacher reassignment in particular. Where we differ is basically define a unique problem with surplus and deficit constraints across schools, and also deficit equalization as an objective, and of course the integrality part, which was not considered in other papers. Yeah, that's it. Thank you. Yeah. Yeah, so he had a question. Yeah.
Can this model also take care of hiring new teachers by introducing a fictional surplus school?
Correct, which has a lot of, yeah, that's a good point. I think it can. Yeah. It's a good point. Yeah. So new teachers who are not yet assigned to a surplus school, I create a surplus school with high enough surplus. Yeah, that's possible. Great.
So something on similar lines. One constraint that you can relax is you're assuming that surplus schools should not become deficit schools.
Right.
That constraint can be relaxed because of fresh recruitments, which happen every year in every state.
Mm-hmm.
So if you relax that constraint,
Right.
will the problem simplify?
So my belief is like if you allow for surplus schools to also become deficit, then I need to look at a different vector altogether, right? Because I can't be just looking at the deficit vectors as my objective to equalize. So I need because right now I'm relying on this fact that all I care about this flows into sync nodes and I leverage Megiddo and so on. So I'm not sure if the current analysis will go through, but I think at some point we thought about it and it was not working out. So that's why, yeah.
So, but if you're introducing the new teachers that are being hired as another extra surplus, then can't you imagine that as a defeating when because you can allow it to go to a deficit, the extra teachers that are needed.
Yeah, so the extra teacher, I mean, so I believe that what he was referring to, like extra teacher is recruited but is not yet assigned a school. So it's intuitive that he should be assigned a deficit school given that there are so many deficit schools in the system or something. So yeah, I mean, potentially we can do that. It's no problem.
Just for teachers in your original model, the acceptable sets can be arbitrary or okay.
Arbitrary, yeah.
So, interestingly, what the result shows, like the algorithm, is that the H star, the original Megiddo, is
Yeah.
actually a very nicely rational
Yeah.
value. So it's
Yeah.
not. Does it say something about the polytopic structure of the thing? So it's
So-
not integral vertices, but
It is integral bodies. So those of you who don't know, for convex game, the extreme points are characterized by the marginal vectors, and so those are the averages that Narahari was talking about, averaging over those vectors, and they're all integral. So that polytop would always have integral extreme points.
But no, not that polytope. Like even I include the final flow graph I look, which gives you the
The residual thing.
yeah.
So that polytop would also have integral extreme points.
One, the rounded one, but others as well.
Yes, all of them. That's why we get the max flow to be integral also in that. Yeah. Yes, that will also be integral.
But it's interesting that the Megiddo Lorentz is very nicely rational. I mean, the denominators are just primarities of
They are fractionals.
Yeah,
they're
very
fractions.
good fractions.
Yeah, they're very good fractions. Yeah. So in fact, it's quite possible that in the first round itself you have D1 equal to D, the entire set of schools, and the equal division actually lies in the core. In that case, it's just 1 over L. That's it.
This Lorentz dominance is necessary and sufficient for strategy proofness?
No. That's clearly not true. So you can define many mechanisms which will be strategy proof in this model and so on. What's interesting is that the Lorentz dominance one is also strategy proof. So that's interesting.
The proof is simple.
So in these models where you have these preference restrictions like acceptable or not acceptable, it's easy to achieve incentives. So it's kind of in that spirit. So in general, you get into trouble in these models if you have strict ranking of, if teachers have strict ranking of deficit schools, for instance, we would have to do something like a deferred acceptance type thingy and so on. But this is kind of going away from those kind of things because we have this restrictive preferences.
Let's thank the speaker.
Thank you.
So we'll break for lunch now at the lawn and we'll reassemble at 2 for the next session.
Welcome back, everyone. I hope you had a good lunch. We have two exciting talks now, and you have the tough battle of fighting your desire to sleep. But I promise these are going to be very exciting talks. First one is by Dr. Hanane Akrami. She is a postdoctoral researcher at University of Bonn and also a Minerva Fellow at Max Planck Institute. She earned her PhD from Max Planck Institute of Informatics. So with that, I'll over to you, Dr. Hanane.
Thank you very much. Hello everyone. I also want to start by thanking the organizers for organizing such an amazing event. and bringing us all together in this beautiful campus of IISc. It's a great pleasure to be here. Thank you. So today I want to talk about equitability of matroids, which is a joint work with Siu Liu from CMU, Roshan Raj from IIT Bombay, and Laszlo Beg from University of Bonn. So this problem can be seen like from pure matroid theory point of view, but it can also be seen from a fair division point of view. And given that I think the audience will be more interested in the second perspective, I will focus more on that. So let's get started with like classic discrete fair division problems, in which as an input we are given a set of n agents, let's say these, and a set of m indivisible goods. So think of these as indivisible items such that each item as a whole must be allocated to one agent. And also each agent I is equipped with a valuation function vi, which we assume is monotone for now, which shows how much this agent likes each subset of the goods. So here you see the value of each item for each agent, and in case that the valuation functions are additive, you already have access to all these VIs. So this is the input, and the goal is to find a fair allocation of the goods to the agents, and an allocation is simply a partitioning of these goods into n bundles, x1 up to xn, so that xi would be allocated to agent I. So throughout the talk, I will be talking about complete allocations in which no item remains unallocated. So now what do we mean by like fair allocations? There are different classes and notions of fairness, and I will be focusing on envy-based notions in this talk. And well, the most intuitive notion in this class is envy-freeness, which is saying that no agent should envy another agent. So vi of xi, which is the valuation of agent I for her own bundle, should be at least as much as vi of xj for any other agent j. Well, as we all know, it's not difficult to see that in this discrete setting that we are considering, envy-free allocations do not always exist. Simplest counterexample, you have two agents and one item which is valuable to both of them. No matter to whom you give this item, the other agent is envious. So we need relaxations of this notion. And there are different relaxations, EFX, EF1. In this talk, I will be talking about EF1, or envy-freeness up to one good. So under this notion, envy from, let's say, agent I to agent j is allowed. Well, as we saw, it's inevitable. But any such envy must be removed upon the removal of some item from j's bundle. So if agent I is envying agent j, then there must exist a good g in xj such that after we remove this item, then the envy is also gone. So the counterexample that we had before for envy-freeness is not a counterexample for EF1, because although one agent is envying the other, upon the removal of the apple, envy is also gone. And well, it's not surprising that this allocation is EF1, because, well, we already know that EF1 allocations exist when agents have monotone valuations, and in fact when they have something more general than monotone, like what we call doubly monotone valuations. So in the case of monotonicity, when the valuations are monotone, this problem is pretty much resolved. So why did I even bore you with all these definitions? Well, the reason is that we are actually considering the constrained fair division setting. So far I only said that the allocation has this property that it must partition the items into n bundles. Like, there are no constraints on what these bundles can be, but in real life scenarios, we very well might have restrictions on what these bundles are or how they can look. For example, maybe some items are conflicting and they cannot appear in the same bundle. Well, you can think of like allocating time slots. Some time slots might be conflicting, and we don't want to allocate them to the same agent. Or maybe we have an upper bound on the number of items that we want to allocate to each agent, and so many of these type of constraints. Both of these and many more can be captured if we assume that there is an underlying matroid on the set of the items, and then we want the bundles that we are allocating to the agents to be independent sets of this matroid. Now, let me first define what matroids are. Well, a matroid consists of a pair EI, so E is the ground set and I is a family of the subsets of this ground set, which we call independent sets. And then if this pair has the following conditions, satisfies the following conditions, then it's a matroid. Well, first of all, the empty set must be independent. If we have an independent set, all its subsets are also independent. And finally, we have the exchange property for matroids, that if we have two independent sets I and j, let's say the size of j is larger, strictly larger than the size of I, then there exists an element in j, not in I, that if we add it to I, we still have independence. So this is the definition of matroids. By the way, feel free to interrupt me and ask questions at any point if anything is not clear. An example of a matroid, like a subclass of matroids, are graphic matroids. So if you are not really familiar with matroids, from now on, whenever I say matroid, you can have this example in mind. So a graphic matroid is defined on a graph. The ground set will be the set of the edges of this graph. And independence is defined by not having a cycle. So any forest in this graph would be an independent set. And then one more definition, and the basis of a matroid is an inclusion-wise maximal independent set of the matroid. So again, coming back to graphic matroids, the basis, the set of all bases of this matroid would be the set of all spanning forests of this graph. And by the third property, it's not difficult to see that the size of all bases are the same. Any questions about the definition of the matroid? Okay, so coming back to our constrained fair division problem. So here we have, as before, we have our set of n agents, our set of items, and our valuation functions. But we also have a matroid defined on this set of items. And now we call an we want the allocations which are feasible. And feasibility is defined as, well, this B consisting of B1 up to Bn, first of all, must be an allocation, meaning that must be a partitioning of the goods into n bundles. And moreover, we want that each of these Bi's to be an independent set in this underlying matroid that we have. In fact, we can, it's without loss of generality to assume that we want exactly basis of, so we want the bundles to be basis of this matroid. And now again, our goal is to find fair allocations, but this time fair feasible allocations, such that each bundle is a basis of the underlying matroid. And by fairness, I want EF1. So some previous works on EF1, assuming that we have this matroid constrained problem. So EF1 exists on the partition matroid constraint, so I'm not going to define these different subclasses of matroids, but for some subclass of matroid, we know that EF1 exists if we have additive valuations. It also exists on the laminar matroids for identical additive valuations. And then so far we are assuming that all the agents have the same, basically the underlying matroid is the same with the view of all the agents. Now this can be slightly relaxed by having a partition matroid with heterogeneous capacities for different agents. And finally, like the only thing that we know about general matroids, not any specific class of matroids, but general matroids, is that half EF1 exists. So we want to get exact EF1, and we, yes?
So are all of these allocations complete?
I mean, so if you want the bundles to be independent set, first of all, the ground set we must be able to partition the ground set into independent sets. And I think if that's the case, then yeah, these are complete allocations. And yeah, we also want complete allocations, so I'll come to that we also assume that.
One much stronger result is possible if you don't want to complete this. You can actually get EFX for all downward closed.
I see.
Very strong
Okay.
result. If you allow for partial allocations and charity, then you can actually get like feasible EFX kind of guarantees.
And what, like what condition on the charity? Because like
You just don't envy the charity.
Ah, I see. Okay. Okay. So, yeah, we are after exact EF1 allocations and arbitrary matrix. We don't want to have condition on what subclasses of matrix we are considering. So let's consider possibly the easiest example that we can think of, that we only have two agents. These two agents are identical. They have identical valuations and they have binary valuations. So basically there are some items that are of value 1, some items are of value 0, and these two agents agree which items are of value 1 and which are of value 0. So this seems to be a very easy example. And then we have the same constraint that we had before, that we want each of these two agents to receive a basis of this underlying matroid. And now the goal is to find a feasible EF1 allocation in this setting. Well, as discussed previously, if we want to have a feasible EF1 allocation, in the first case we must be able to have a feasible allocation. So meaning that this matroid we must be able to partition it into two bases. Even forget fairness, at least there must be two disjoint bases B1 and B2 that partition this ground set. So this is clearly a necessary condition, but is it sufficient or not? So this is the fair division formulation of the problem. Now let me also give you the formulation of it that has been there in the matroid theory literature. So it is called equitability conjecture. Let's say that we are given a matroid and we know that the ground set can be partitioned into two bases. So the necessary condition is there. And now we have an arbitrary set S. Now the goal is to find two disjoint bases that equally divide this set S among themselves. So knowing that this pair A1, A2 exists, that partition, so A1 and A2 are both bases and they partition the ground set, and we have some arbitrary set S, we want to find another pair of bases, B1 and B2, that equally divide S. So I claim this is exactly the problem that I defined in the previous slide. Namely, you can think of this set S as the set of the items that are of value 1 for both of the agents. And then EF1 means that this set must be equally, or in case that the size of S is odd, almost equally divided among these two bases. Okay, so the main result is that, well, we prove that equitability conjecture is true, and in fact this necessary condition that we have is also sufficient to get equitability. Okay, so for the next maybe 10 minutes I am going to give you like the roadmap of the proof of the equitability conjecture without getting into any technical details of the proof. So we define exchangeable sets as following, that we have this basis A1, A2, and we say that a subset X of the union of the two is exchangeable if, well, simply we can exchange whatever is intersecting A1 with whatever is intersecting A2 and still have a pair of bases. So basically here X is intersecting A1 in these dark green elements and A2 in light green elements. And after swapping these elements, we still want to have a pair of bases. So clearly X must intersect both of A1 and A2 equally, but that is not a sufficient condition. But if that is so, then we say that X is an exchangeable set. Now, remember what we had? Well, the picture that we were beginning with was this. And we want to find a pair of bases that equally divide S. Now consider the following, that we can find an exchangeable set X such that all the elements but one element in X are red, meaning that they are in S, and there is only one element in X that is not in S, is not red, and that one is in A1, the set that has less number of red elements. So if we can find such an exchangeable set, then after the exchange, we get a partition that, compared to one step before, divides these red elements more equally. And the reason is that, well, as you see in this picture, well, X is intersecting A2 in 2 elements here, but let's say K elements. And it will intersect A1 in K minus 1 red elements. So after the swap, the number of red elements in A1 increases by 1, exactly by 1, and the number of red elements in A2 decreases exactly by 1. So now our new goal, and so we are after finding such exchangeable sets, which we call TS exchangeable sets, for S being, well, yeah, the set that we want to divide equally, and T being the one element that is not in S but in A1. So now what we want to prove is that as long as A1 and A2 are not equally dividing S, we can find such an exchangeable set, such a TS exchangeable set. So that is our new goal. Now, in order to prove that, well, we need this concept of exchange graphs. So given two bases, A1 and A2, the exchange graph on A1 and A2 is defined as following. So it's a bipartite graph, and on one part, the elements correspond to the elements in A1, and on the other part, the elements correspond to the, the vertices correspond to the elements in A2. And then there is a directed edge from X, let's say in A1, to Y in A2, if the following holds. So this directed edge means that we can remove X from A1 and add Y to it and still have independence, or still have a basis. So these edges are defined both ways, like from A1 to A2 and from A2 to A1. And now I claim that, well, what we were after was like this set of TS exchangeable sets. And now I claim that what we actually need, or it suffices to find something like TS cycles in this graph, and that would give us a TS exchangeable set for free. So what is a TS cycle? By a TS cycle, I mean a cycle that has all its elements are red except one element T, which is also in basis A1. So I'm not going to prove this, but a rough intuition is that if you consider the minimal cycle like this, that itself is a TS exchangeable set. Well, you can remove T and add this element, and you know you have independence, and then you're removing this from A2 and adding this, and you know you have independence, and so on. So now our goal is to find such a cycle, and now I'm just going to give the proof itself is very short, but I will just give a proof idea of it, and that is that we consider so let's look at the induced graph on red elements only. So we know that these red elements are more in A2 than in A1. Therefore, there must exist a strongly connected component of these red elements that intersects A2 more than A1. So now let's such a purple set be that strongly connected component. And now I claim that all we need to prove is that there exists an edge from this set K to some node outside K in A1, and from this to, again, back to the set K. And why is that so? Well, if these two edges exist, then I know that Y and Z are in the same strongly connected component. So I can just find a red-only path from Y to Z and close the cycle that we were looking for. Now I will not bore you more with like proving that these two edges actually exist, but the proof is very short. Okay, so yeah, well then by doing that, by proving that these two edges actually exist, then we prove that equitability conjecture is true. Let's see the statement once more. Well, if our ground set E can be partitioned into two bases, then for any arbitrary set S, subset S that we have, there exist two disjoint bases that equally divide S. Yes?
So in that graph, you only capture one item exchange. So if there are, let's say, two items here in A1 and two items here in A2, such that you could exchange them together, is it also true that you could do one at a time and the sets are going to remain independent throughout?
No, that is not true, and that is in fact that is a big conjecture. So what we prove is that there exists like a big set that you can exchange and then have independence, but we cannot prove that you can do it one at a time, and that's actually a big open problem whether that is possible or not. So these like White's and Gabo's conjecture are like, both of them are something along those lines that you're saying. We can discuss it offline if you want, and both of them imply this, and they are still open, but this does not imply that. Yes, and in fact, okay, first of all, yeah, we have this result, and these B1 and B2 can also be computed in polynomial time. Well, simply because we proved that such a cycle exists, and finding such a cycle can be done in polynomial time. And this can be easily generalized to K when we know that our ground set can be partitioned into K bases, and now we want to find K bases that equally divide S. And it's actually pretty simple. As soon as we have the 2, it's pretty simple to get it for K, because as long as you have this inequitability, just limit your focus to two bases, one that has minimum intersection with S and one that has maximum intersection with S. And then by using the result for two bases, you can equally divide them, and by keep repeating it, we get the result here. And this is exactly equivalent to the EF1 problem that we had in the beginning, that we have a matroid constraint for division, and the agents are identical and have binary valuations. And now if we know that a feasible allocation exists, then we prove that also an EF1 feasible allocation exists. And from this, we can also easily get that EF1 allocation exists for two agents with binary valuations, not necessarily identical, because we can do this cut and choose protocol. Like, we only consider one agent. We know that for identical valuations, an EF1 an EF1 allocation exists, so we can get a partition such that agent 1 is happy getting either of the bundles, and we let agent 2 to choose which bundle she wants. Okay, so
but the
yes.
matroid constraint is the same for both.
Yes, the underlying matroid is the same for both.
Isn't that EFX?
It's not EFX because the other, okay, it depends on the definition of EFX. EFX 0, EFX plus, because if the number of one elements is odd, then by removing an item of value 0 from your bundle, I'm still ending. Yeah. Okay, so so far I talked about like one equitability, like we only have this one set S that we want to equally divide, but we can also define two equitability, three equitability, and so on. So here in two equitability, we assume that we have two disjoint sets S1 and S2 that we want to equally divide among two bases. So yeah, the condition is the same as before. We know A1, A2 exists. We can partition the ground set into two bases, but then do such bases also exist that equally divide S1 and S2 at the same time? Well, our first result is that matroids are in fact not two equitable. So they are one equitable, but they are not two. And the counterexample is very small, and in fact is a graphic matroid. So the counterexample is this K4. So the set of the elements is the set of the 6 edges that you see here. And first of all, the necessary condition is there. It can be partitioned into two bases, one basis being this, and the complement of it is also a basis. Now let's say that we have S1 is the set of these red edges and S2 the set of these blue edges. So what are we after? We want two bases B1 and B2, each of them having exactly one red edge and exactly one blue edge. And this is not possible. So let's say without loss of generality, 1, 2 goes to B1, 3, 4 to B2. Everything is symmetric so far, so without loss of generality, let's say 1, 3 goes to B1 and 2, 4 to B2. Now, B1 is not going to accept 2, 3 because then it's not independent, it won't be a basis. So we must give 1, 4 to B1, but that leaves 2, 3 for B2, which again gives us something that is not a basis. So in this simple example, there is no way of finding two bases that partition the ground set, and each of them has exactly one red element and one blue element. So matroids are not two equitable. But that is not the end of the line. What we prove is that matroids are almost two equitable. So what we prove is that we have S1, S2, we can equally divide S1. And for S2, ideally we want to have that B1 intersect S2 is exactly S2 over 2. But what we get is an additive error of 1 here. So maybe in the worst case, the picture that you get is something like this. That instead of having equal number of S2 intersect B1 and S2 intersect B2, you have on one side 2 more than the other side. And this gives us some fairness implications. So what we prove is that, again, coming back to like matroid constrained fair division instance, now here if we have identical but tri-valued valuations, so tri-valued meaning that each item can have value A, B, or C. So in binary we only had 0, 1, and now here we have more degree of freedom. And even in this case, we prove that EF1 allocations exist. So the first corollary we had for one equitability, for EF1 for binary valuations was exactly equivalent to one equitability. This is not equivalent to 2 equitability, but we use that as a tool to get this result, to improve this binary valuations to tri-valued valuations. So let me skip the proof sketch of this. It basically uses this 2 equitability result together with the exchange lemma that we had. But let me recap our results and most importantly go into like future directions. So our main result is that all matroids are equitable, and then we also prove something similar, or actually what we prove for 2 equitability is also tight, that matroids are almost 2 equitable. And we also get applications of this in fair division, namely that EF1 allocation exists for tri-valued identical valuations. Now, for future direction, well, I talked about 1 equitability, 2 equitability. Well, you can define L equitability in a similar fashion. So now we have that our ground set can be partitioned into K disjoint bases. And we also have L disjoint subsets, S1 up to SL, that ideally we want to equally divide among all these K bases. So ideally what we want is that for all I and J, Bi, the size of Bi intersect Sj is exactly the size of Sj over K. But we already know that for L being 2, it's not possible. Like here we get an error of 2. Now, the question is for arbitrary L, what can we have here? And we conjecture that what will be here can be bounded by a function of L, like the number of sets that we want to divide equally. But what we know is that f of 1 equal 1 works, f of 2 equal 2 works. For f of 3, we do not have any bound on f of L. Like we don't know even if f of 3 exists or not, or maybe it will be bounded by the number of order of the size of the elements. So that's the first thing, like looking at it from some really pure matroid theory open problem. Yes?
If sets are not disjoint, then there are counterexamples?
We don't have any counterexamples now. But even if sets are not disjoint, even for f of 2, we don't have any bound. I think the best counterexample we have is that K4.
Aren't those counterexamples like upward close? Like, does it also not say for L equal to 3, put empty set?
I mean, for L equal to 3, it says that you cannot get better than 2, because you can also think of the black edges as the third set that you want to divide equally. But it doesn't give anything better than 2, or we don't have any example that says anything better than 2 for 3 equitability. And now, like coming back to the fair division problem that we were having, so for a matroid constrained instance with 3 agents and binary valuations, we don't know if an EF1 allocation exists or not. So what we show is that for 2 agents and binary valuations, EF1 allocation exists, but even 3 agents and binary valuations, well, non-identical. For identical, we know it exists, but non-identical, this is open. And also, so this is basically really the first step after taking that, okay, we know for 2 agents it exists, but for 3 agents we don't know. And also, again, like taking like one step further than what is already known, we know that for 2 identical agents with tri-valued valuations, EF1 exists. But again, if we have 4 valued valuations, we don't know whether it exists or not. So this would be something stronger than 3 equitability. No, something that can be implied by 3 equitability, but yeah, even this we don't know. Okay, with that I conclude my talk, and thank you for your attention.
If you assume Gabos conjecture, then what value of FL do you get?
If we assume Gabos conjecture, we get EF1 for additive valuations. Yeah.
Before time, so these questions.
Yes.
Great. Could you give me some intuition about why the 2 equitability error is exactly 2 and not maybe higher than that?
Yes, I actually can. So the way that we prove this 2 equitability, after you have this exchange lemma, it's not difficult to prove this 2 equitability, because the exchange lemma is saying that you have a set S and it's not equally divided, and you can make one step progress, like one, and depending on like how your state looks like, you take that S to be either S1 or S2 or the complement of the 2. And the worst case is exactly when we are here. So from this state, you might not be able to make any progress. Because if you take S2, maybe you pull something from S1 back. But anything but this, you can make improvements.
Okay. Sorry, I'll wait for other questions.
Okay.
All right.
I think we can.
If hypothetically you were to restrict the matroid on the sets, if you were to restrict the matroid on S1, so you get 2 different bases of 2 different matroids, presumably, if that makes sense. Like if you were to remove the elements of S1 from your set, and you'll create 2 different matroids where the first one will be independent of the one and the second.
Yes.
Would the exchange lemma still work, or would that?
So if I get your question correctly, you mean like ignore S1, do equitability, and add S1 back?
Yes.
So the problem is that if you add it back, you might not have basis anymore.
Yes. Okay. No, I'll talk to you about it offline.
Okay.
It's a little more complicated.
Okay. Yes.
So if agents here, instead of being identical, it just had like scaled up versions of the valuation of the 6, it should work, right?
Yes, it should. I mean, scaled up. So the good thing about EF1 is that it's a scale invariant, so you can always, yeah. Yes.
Do we know anything if there are different matroids?
So for different if like agents really have different underlying matrices, I don't think we know anything. The most general thing I could find was this, that you have, so the third, that you have a partition matroid but the agents have heterogeneous capacities. So you have for each BI you have different constraints, but still you have a partition matrix.
If you allow for charity, it again works for as general as you can. It actually works for all downward closed heterogeneous constraints.
I see. But I mean, if you allow for charity, then you are relaxing on having a basis, right? So you're having.
You just define something called feasible NV freeness, and you get as strong a result as you can imagine.
Okay, interesting.
The charity is next to godliness. It gives you everything.
Okay.
You can have heterogeneous downward closed constraints, and you just compare NV against feasible sets. You have EFX actually, not just EF1.
Okay.
But the feasibility, is it coming from independent sets because of the partition?
Downward close. Any constraint where if a set is feasible, it's subset. So not just matrix, just the second property of matrix, not even any set.
Nice.
Okay, if there are no more questions, it's time to
Thank you. Thank you very much. Nice talk.
Okay, so next up we have Dr. Shivam Gupta. Shivam is a postdoctoral researcher here at IISc with Siddharth, and he did his PhD at IIT Ropar under Dr. Shweta Jain, where he was also the Prime Minister's Research Fellow. So with that, I'll invite Shivam to speak about.
Good afternoon, everyone. Good afternoon, everyone. Today I would be discussing one of the work which is like diversity into similarity search. This is joint work with Professor Siddharth and Nirjar. Both of them are present over here, and also with Kiran from Microsoft Research. So when I say this nearest neighbor search, so what particularly I mean is that I would have some bunch of input vectors, and these input vectors can be something like embedding from different deep learning or generative AI models, and along with that I would have a query vector, and my goal would be something like let's say I want to find 3 most similar vectors to this query vector in my input space. So this would be my goal, and this problem has a variety of applications in real world, and most of the solutions are right now deployed as well. I would give the examples in the upcoming slide. So let's say that first example that we look into is something into recommendation systems. So here what we can look into is like we go to any of this e-commerce platform, and there what we can have is something like input space can be a complete embedding space of different products available with us. And whenever a user types in some query like on the Amazon search engine, like I want to see blue shirts, so this query gets mapped to the same space, and what we tend to do at the backend is like we will try to find some of the most similar products in my input space, and that let's say these are the 2 products, I will be displaying back these 2 products to the user. So it's like we will be trying to find the most similar things to my query vector. Similar things can be seen into the web search as well. Like in web search, my input collection would be something like all the different web pages that are hosted over the internet, and whenever a user types in some query like Amazon, Google and all that stuff, what I will be doing is before applying all those heavy computation like PageRank and all that, I can bring in let's say some 10,000 web pages, and these 10,000 web pages can be buffered to, or we can say transferred to our page ranking algorithms. So These things are being even used right now by Microsoft in their deployed solution in the Bing search engine. Moreover, they are using this for their ad retrieval as well. Similarly, nowadays we are looking at a lot of applications into LLM and all that stuff. There also nearest neighbor search is getting used. So it's like our input space would be different documents or knowledge source that we have, and whenever user types in some query, so in order to avoid hallucination of the models, we will be using some of the domain knowledge available with us. Right now there is one startup which is like Vector X that is using nearest neighbor search in their solution. So having cited a lot of applications for this problem, there are some challenges that arrive when we look at the real world aspects. So the most important challenge is like the high dimensionality of our input space. Like the vectors that we have, they can be into a space which is like as high as 1000 dimensional high. And moreover, as we already know, in all the applications that we saw, which is like Amazon, even the web search and all that stuff, the input size of the vectors, like the total number of vector space could be quite large available with us. Moreover, in all the real world scenarios, what happens is that whenever a user types in some query, let's say I want to look at some products, the user will not be waiting too long for the results. We need to have quite less latency in our solutions. So, but if we look at some problem, like if we try to solve the exact nearest neighbor search problem, then we would need to iterate over all our complete embedding space. That would be taking a lot of time. So what we are mainly doing in our real world deployed solution is that we are looking at a relaxation of this problem, and it is something like we are looking at approximate nearest neighbor. So what we tend to do in approximate nearest neighbor is that we will try to find some set of vectors which are having good approximation to the optimal, or we can say the best nearest neighbor. We will try to approximate that thing, and this problem is this problem is almost a decade ago problem, and there are many I would say many solutions available for this problem. Like there are many clustering based solutions coming up, even there were some hashing based solutions, and recently even Microsoft has deployed a graph based solution which they call as disk ANN. So this is already being deployed by Microsoft in their Bing search engine. So this is a very well studied problem, and moreover, over time different organizations are coming up with some challenges at different flagship conferences related to solving this problem. So we can say that this is a very I would say deployed solution used in many of the application. But now we will be looking at something like how we can connect this problem to diversity and fairness aspects. So my problem would remain same itself, that I want to find some k vectors that are more similar to my query vector. But now what would happen is that with each of my input vector, I would be having some attributes associated with it. So these attributes can be something like there can be some color, some year associated with my products. So what my desirable goal would be, I want to return some set of nearest similar neighbors, but in this return set I want to increase my diversity as large as possible across these attributes. So there are many different real world applications that are coming up recently that has tried to accommodate this diversity into their solution. Like what Google has started doing is that you would be having certain restriction on the number of I would say web pages from a single domain. That is, you won't be seeing so many results from a single domain. And even Microsoft in their this ad recommendation, as I mentioned, they have started restricting the number of advertisements. Let's say you won't be seeing more products from Samsung only. You would try to maintain diversity of across different brands. So what they are doing is that they are mainly coming up with some constraint based solution. So you would be restricting, let's say you would have maximum of 4 ads from one brand, let's say Samsung. You would be having some constraints on that thing. So our problem is something like you want to retrieve the k most similar vectors, but you won't be retrieving more than k prime vectors from each attribute. So there are many different implementations that have been looked into. So one of the implementation that Microsoft right now is deploying is something like a graph based solution which they call diverse ANN. And even in this work, what they propose is that what we can do is we can have some post filtering based solution. Let's say you want to show user some 10 most similar results. What you can do is you can bring in or fetch some 100 results, then you can filter those results and try to accommodate your diversity constraints. But there are some challenges in this constraint based solution. So it's like I would be discussing these. So these are some of the experimental results that we observed on the Amazon datasets. So this is not a stylistic example, but this is something like what we actually obtained when we experimented on the Amazon dataset. Let's say that we are looking for some products into the product space, and we will be looking at attribute something like color of the product, and we want to improve our diversity on that color. So what we saw in our experiments is that if user makes some query like shirt, then things are good to go. Like you would have diversity over different colors, like the solution would have red color, green color, and many more colors available with you. But if you looked at something like query like blue shirt, and you put a hard constraint of let's say 4 on your solution, then the neighbors that are from 5th to 9th, let's say you are fetching some 9 neighbors, so the neighbor 5th onwards would not be from definitely blue color, because you have a threshold on the maximum neighbors that you can fetch from blue color. So what we can say is that these threshold based or constraint based solutions mainly do not adapt dynamically to different queries, like when we want relevance and when we want diversity. Like here we wanted diversity, and in this query we mainly wanted to focus more on the relevance rather than the diversity. So it does not dynamically adapt on that thing. And one more biggest challenge is that how to choose this k prime value. Like here we were only dealing with one thing, which is like color. So okay, we could decide, let's say keep it 4. That is also ad hoc. There is no heuristic or method available how to decide on that. But if we look at something like we are looking at multiple attributes like color and year as well, then it's quite difficult to choose this value. So we solve this problem from a economic perspective. So what we do is we mainly say that all the different attributes that are available with us as different agents, we will be treating different colors and brand as different agents. And what we will be doing is that these agents will be deriving some utility based upon the final set that we are returning to the user. So it's like, let's say that we have some input vector space which is like P, and let's say that there are some C different attributes available with us. So our goal would be to find a subset of this input vector space. Let's say that this subset is S, and we are given a query Q, and what we want to do is, like this is a diversity problem. So what we will be saying is that with each input vector we will be having some attribute associated with it. Let's say that there are as we mentioned that there can be C different attributes. Let's say that any vector V takes one of the value from this set 1 to C, and how we will be defining our utility is something like, so whenever I select a vector, let's say in my solution I select some vector V, so this vector V would have something like an attribute associated with it. Let's say this vector V belongs to red color, so this vector V in my solution will be adding to the utility of the red color. So it's something like if I have 4 neighbors belonging to red color, it would be adding to the utility of these 4 would be adding to the utility of my red color, something like that. So in this setting, if I define the standard nearest neighbor problem, it would be something like I want to find a subset in my space of cardinality k such that I maximize my social welfare, which is like the sum of utilities over all these colors. And if I add some constraints to this problem, then it would be something like from each attribute I can have maximum of some k prime vectors that I can fetch in. So this would be some standard problem that people were looking right now, even in the diverse NN problem. So what we will be doing is that we will be looking at this problem from a very different perspective. So we very well know that in this welfare economics we have different utility functions to mainly aggregate our utility. One that we already have seen is like a social welfare kind of thing, where we will be just summing up all our utilities that we are fetching. Other than that, we have a lot of other welfare functions available with us, like one famous welfare function is like Nash social welfare. So where rather than looking at the sum over all the different colors, we will be focusing over the geometric product of the utilities. Similarly, we very well know that we have other welfare functions like egalitarian welfare as well. But particularly in our work, we are focusing on Nash social welfare. And what would be our problem is that we will be having the same utility setup, but rather than focusing on social welfare, we will try to find a subset of size k such that our Nash social welfare is maximized. And here I am adding a small smoothing parameter just to ensure that this product does not degenerate to 0. So the main reason for choosing this Nash over here is that this Nash satisfies a lot of, so its Nash is only the welfare function that satisfies a lot of fairness properties. So that's why we looked into Nash social welfare for this problem. And so these are some of our theoretical contributions. So when we look into our setting, which is like single attribute setting, that is each vector v is associated with only one attribute, like we are only dealing with, let's say, colors at that time. So in this setting we have a greedy algorithm that achieves the exact solution, and the results adapt to approximate oracles as well. So let's say if we have two approximate oracle, then this wrapper over this Nash wrapper would be finding that two approximate solution only. Since our algorithm is a wrapper over the existing ANN based solution, so we are having an additional runtime of like k plus c log k. Here k is the number of vectors that we want to retrieve, and c is the number of different agents that we have. So here it can be something like, say, this is a single attribute setting, so it can be, let's say, the number of colors that we have in our system. And in multi-attribute setting, let's say when these input vectors are, each input vector is associated with, let's say, some different color and brand as well. So it's like the number of attribute for each vector can be more than one. In this setting, we show that the problem is NP hard, and right now we have a polynomial time algorithm that achieves 0.63 of approximation factor to the logarithmic of the objective function, like it's the 0.63 approximation to log Nash social welfare. So we even extend our setting from Nash social welfare to p-mean welfare as well. So in place of Nash social welfare, we will try to maximize the p-mean welfare. So this mainly comes from an industry perspective as well. Like industry might need to tune their deployed solutions in a way that they may be focusing more towards the revenue and all that. So what they can do is they can tune this p parameter. So if p would be equal to 1, it would be going towards the social welfare, and if they are tuning p towards, let's say, almost minus infinity, then the solution would be focusing more towards the egalitarian welfare. Mostly we propose that we should use p equal to 0, and I would be showing some of the experimental validation as well, where we can see that p equal to 0, which is Nash social welfare, it achieves almost Pareto solutions. So a quick recap before I discuss the experimental results is like, earlier we were having some threshold based approach to diverse nearest neighbor problem which suffered different challenges, and Nash offers a promising solution to overcome these challenges. And some of our theoretical results were like the Nash based formulation adapts a optimal algorithm for single attribute setting, and this formulation easily extends to the multi attribute setting. So this multi-attribute thing is right now in something that industry is looking forward, and even we are in a process of validating our this results with Microsoft Research, and we are quite hopeful that it comes into deployment. Microsoft already has some of the solutions for single attribute setting, but they are looking for at least multi-attribute setting. They are actively looking for the different solutions. So now we will be looking more towards the experimental validation. So here we can see that something like these are some of the results that we look into the Amazon product dataset. So let's say that you are trying to fetch some 9 neighbors from the dataset. So these would be some of the results, like in standard ANN solution, when you were not looking at diversity into account. So what was happening is that most of the neighbors that were coming up, they were from black or white color only. So if we look at the Nash based solution, then there are some nearest neighbor that are from black and white color, but we are able to fetch in the diversity on color as well in the 9 neighbors that we are bringing in. Similarly, if we fetch on some query like blue shirt on standard ANN solutions, so we can clearly see that almost 9 neighbors are from the blue color, and this was something that we need to keep intact in our Nash solution as well. So here we can see that these are some of the results that we get from our algorithm. So it's like almost all the 9 neighbors are from blue color. So what we can see is that now Nash easily adapts between the relevance, between diversity and relevance, which was not the case in the threshold based solutions. There we were getting harmed in such a solution, like there we were only getting first 4 solutions to be blue color only. But now it is easily adapting between both the things. So now we will be looking at some of the Pareto curves. So let's say that on x-axis we look at something like approximation ratio, which would be something like a metric for measuring the similarity or relevance. And on y-axis what I would be taking is like a metric for entropy, which is like the diversity metric. And what I want is, I want a solution which is high on approximation ratio as well as high on diversity. That would be something that I would require. So these are some of the results on one of the dataset, which is like Amazon dataset. So this is like the standard ANN solution when you are not looking at diversity into picture. So you would have high similarity in your return set. The similarity is almost close to 1. But the entropy, which is like the diversity in the solution, is almost close to 2.8 or 2.7, I can say. And next is something like div ANN, which is the solution that was currently being deployed by Microsoft. In this solution we had to provide a threshold that I mentioned earlier. So let's say if I take a threshold of 1, which is like from each color I want only one product in my solution, so it would have highest entropy, which is like highest diversity, because I have only one product from each color. But it would be slightly trading off on the similarity, because I might be now bringing in some products that are not that relevant just to capture my diversity. If I relax on this threshold parameter, let's say I keep on relaxing on this threshold parameter to 2, 5 and 10, so I can see this curve. So this curve is capturing that fairness and efficiency trade-off. So it's like as soon as I am increasing my this threshold, I am almost reaching, which is like the standard ANN solution. And this Nash sits over here, like it captures both high entropy as well as almost 95%, 94% similarity it captures. So it's like it's kind of Pareto dominating on the data set. As I mentioned that we can even extend our results to p-mean welfare. So these are some of the results on p-mean welfare. So this is the most diverse solution and this is the most relevant solution. So we can tune our p parameter, and this would be some we can say we can say a curve over our solution, like p equal to all minus 10 would be going more towards the most diverse solution, and as soon as I'm setting my p equal to 1, it would be matching the standard ANN solution. So we have results over different real world data sets. And next I would be discussing some of the results into the multi-attribute setting. Here we can see that let's say we look into something like color and brand together. So for this experimental setting, what we are doing is that we are right now, since it's not properly defined how we can have this threshold for different attributes. So what we are doing for this experiment is that we are setting the threshold same for this color as well as brand. So let's say if we have a threshold of 1 for, let's say, both color and brand. So these are the some of the results. So here we can see that this Nash, which is like p equal to 0, this is achieving almost close to 98% relevance. At the same time, it is having quite good entropy. But if we go for some threshold based solutions, then we need to relax the threshold almost like 20. That is, we are giving a relaxation of 20 to color, each color, and 20 to each brand as well. So in that way, it's quite high relaxation compared to the number of neighbors that we are getting. So in this experiment, we were fetching, like, let's say 50 neighbors, and out of those 50 neighbors, we are almost relaxing like 20 neighbors can be from the same color. So it's quite a big relaxation, but Nash is able to capture that thing without any threshold mechanism. Similar results we observed on over all the attributes, like let's say this is over the attribute 1. So in this dataset we were having 4 attributes. So we were having a Pareto solution for over all the 4 attributes. So right now we are looking into some of the future direction into this work. As I mentioned that we have some indexing based solutions like the disk ANN solution. So right now we are looking into something like, can we design a graph based solution where during the search of this graph itself we can satisfy Nash social welfare. And also we are a good future direction can be to look into setting where these attributes are not explicitly defined, like images and all that stuff, where we don't know the attribute information like color and brand, how we can define these agents and all that stuff over there. So yeah, I'm open for questions.
What was the C you used in the Nash welfare? If you go back to the objective function for Nash, what was the C there?
So sir, C would be a different type of agent. So in our data set, it can be, let's say, in a
type, it has economic factor. It's just the number of attributes. Every attribute is an agent.
You're not optimizing over the C.
No, it's a given. It's a given. If you have a product catalog with 30 colors, you have 30 Cs. So for every color, black, white, blue, yellow, you pick a product of that color, it adds to its utility. So among these 30 agents, i.e. 30 attributes.
So you're just maximizing the product. I mean, you're not weighting them, just maximizing.
I'm just maximizing geometry, the product, Nash welfare. Every color is an agent, and I look at Nash welfare.
Well, that seems like a natural thing to do if you want diversity, right?
Now it is. Yeah. Not to like a big industry, but now it is.
Yeah.
You mentioned Microsoft is using this nearest neighbor,
So-
similar to nearest neighbor algorithm.
Sorry, I cannot hear you.
You mentioned Microsoft is using nearest neighbor sort of algorithm in Bing.
Yes.
Do we know what is the other one?
Amazon.
What's
So
the
there are like not just one Bing, but even the ad recommendation systems use it across. So Meta, for example, has the same thing. The ads that you see, the initial pool comes through this, and then you run either a first price or a second price. So it's being used in almost every sponsored search ad engine, including Meta and Amazon.
No, for Amazon, because I feel for any product-based industry like Amazon, it's really more relevant because you're just buying
Bing is using in ag right now ANN graph-based solution. Meta is using clustering-based solutions for their purposes. Like they are not focusing on graph-based solutions; they are more toward the clustering-based solutions.
Wait, let me clarify. Graph-based for ANN itself. So
Yeah.
they are, I mean, her question is, where is ANN being used?
Okay.
It is being used throughout, and at different stages through different implementations. So the implementation could be either
Clustering-based or graph-based.
but it is ANN.
More questions? We are way ahead of time.
That's not a bad thing.
If no more questions, let's thank the speaker.
Hi, it's my pleasure to welcome Pooja Kulkarni to be our next speaker. Pooja recently completed her PhD from UIUC in computer science, and she's currently a postdoctoral researcher at Northwestern University. Her work is in fair division for beyond linear valuations, fair division in online settings, and economics of data and digital goods. Prior to this, she did her master's here at IISc, where she was the gold medalist in her batch. Today, she's presenting one of her recent works on online fair division. So let's welcome Pooja.
Thank you so much, and thank you everyone for sticking around to the last session. I know people will be tired, so I try to keep this light. So like Rito said, I'll be talking about my recent work on online fair division towards exposed constant factor MMS guarantees. This is joint work with my very wonderful collaborators, Parnyan Chakar, who is a PhD student at UC Irvine, and Ruta Mehta, who was my advisor during my PhD. So before I get into the work itself, let me motivate the situation a little bit. And so to see this, consider the scenario of disaster relief. So when a disaster hits any region, then people set up relief hubs in places. For instance, Amazon has set up relief hubs across Europe in different parts. Or there is a charity called Global Giving that collects relief materials from the public and will then distribute it to people. So what happens in a disaster relief effort is that these relief centers, they collect a set of goods. So this is a photo of an actual warehouse for disaster relief. And when people come in, they take these goods. So for our purpose, this is essentially an online allocation problem where there is a bunch of goods available offline with us and people come in one by one. We need to allocate these goods to the people who are coming in. So now there is a central planner who is going to allocate these goods, and suppose the central planner allocates the goods in this way. I have color coded the allocation with the agent. So the green agent gets the green goods, the pink one gets the pink, and the blue gets the blue. So these people over here, they are not left with any goods when they arrive, and this is actually they're going to say that it's not a fair allocation. So this will create chaos. We have seen many talks today. We want the society to be stable and good always. It's better for everyone involved. So actually, this problem is not an online allocation problem, but an online fair allocation problem. So if the goods were actually allocated in this way, then all people in the system, in the society are happy. The society is basically stable. There is no chaos, further chaos created. So the problem that we look at is an online fair allocation problem where we have a bunch of goods available offline. There is a central planner who is going to allocate these goods to a bunch of agents who are going to come in online. We don't know how many, we don't know who. Okay, so this is the setting. Formally, if I want to introduce some notation, an online fair division problem consists of three parts. The first is just the division or the allocation part, which has a set of agents, which I will always denote as N, a set of goods, which I'll denote throughout the talk as M, and the agents have valuation functions over the goods VR. So you give me a set of goods, I'll give you a value. So this is what VR represents. Then there is the online aspect in the online fair division problem, which either agents can come in online or goods can come in online or both can be online. And then there is the fairness aspect. There are many fairness notions defined by economists and computer scientists, Nash welfare, NV freeness, MMS APS. We have seen a few of them throughout the day. For the purpose of this talk and this work, I will be focusing on a division allocation problem where the valuations are additive. So each agent and each good, each pair ij has a value wij, and the value of a set of goods is just the sum over these vijs. The online part, I'll focus on goods available offline and agents coming in online, which is the exact disaster relief scenario that I motivated it with. And the fairness part, I'll be focusing on the maximum share or MMS. Many of us know this definition. For those who don't, maximum share is defined per agent basis. So for agent I, it is defined as the max over all allocations, the minimum value that she can get in the allocation. So this share is calculated by the agent I by looking at the set of valuations and saying that, okay, if I could divide this into n parts and I will take the least possible part over here, what is the best least value that I can ensure for myself? So this is very close to what Mula has talked about unanimity, fairness, unanimity testing. So this I think would satisfy for integral allocations. Okay, so these are the notions. Any questions here?
This talk is for goods, not choice.
Yes. Any questions in the definitions themselves over here? Okay, great.
So I didn't understand MMS and then what? What is the fairness?
MMS is the fairness notion. So we want each agent to get her MMS value. Yeah. Okay.
It's shared based.
Yeah. And allocation is fair if everyone gets their fair. I should have specified that. Yeah. Okay, so what is the past work? I'll divide it into two parts. Past work on online fair allocation. There is a lot of work on agents coming online and goods and divisible goods available offline. Okay, so we are focusing on indivisible goods available offline. There is some work done on divisible goods that are available offline. Then there is work on indivisible goods that come online, but agents are offline. So we allocate it. This is main online fair allocation. These are the two things that it has focused on. In MMS for offline setting, there is a lot of work. There is non-existence of MMS allocation. So we cannot actually give an allocation where each agent gets their MMS value. This has been shown. So people go for approximately fair allocations where you want to give some approximate MMS value to each agent. For additive valuations, there is a 2025 paper by Huang and Zhu. It gives a 7/9 approximation. For submodular, there's 10/27. It has been studied for multiple valuation classes. And these are all very recent works. For additive valuations, it's on archive. It came up a few months ago. For XOS subadditive, these are both EC 2025 papers. Online fair allocation is also studied in EC 2025. There was another paper in online fair allocation. So both these problems are individually very well studied. However, there is no previous work on this setting where indivisible goods are available offline and agents are coming in online. So for any fairness notion.
Just the last one, subadditive. What is the statement there?
You get a 1/log n squared allocation exists.
Of MMS or?
Of MMS, yes.
Oh, okay. And for many values of n, this is better than those numbers, but some other values.
No, this is for subadditive, right? For subadditive, this is the best known existence.
Okay. Thank you. Okay.
So it just gets harder to prove existence as we go forward. Yeah. So, but despite so much work in both these parts, there is no work on any fairness notion for the online fair division setting where agents are coming in online and goods are available offline. Indivisible goods are available offline. So this was actually mentioned in a survey by Amanatidis et al. In 2023 that the alternative model that considers a fixed set of resources and agents who arrive and depart over time is not being considered for indivisible resources, primarily because it is very challenging to achieve any positive results in this area. Okay, so why is it hard? Let me just give some intuition. Suppose we have this set of goods available offline with us. Okay, the first agent comes in and she says, I like all of these goods. Give me anything that you think is fair. Suppose I give any set of more than 2 goods to this agent. Okay, so she goes away from the system. She has departed. She has taken those goods with her. And then the second agent comes in and says that, oh, I actually liked only those specific items that you gave away to the first agent. So now there is nothing left for this agent, which makes the agent naturally very sad. And we don't want this happening. And this is a very fundamental problem that unless we know what is going to happen in the future, like if you were a central planner and I just tell you that, okay, give things to people as and when they come, there is no way for you to decide even for the very first agent what you are going to give to this agent. There is no good way to decide that. So what we do is we introduce this new model which we call online K-type FD, so which is online K-type fair division model, where we assume some information about the future is available to us. So in particular, what we do is we know the number of agents that are coming in. Okay, first of all, we know this. Secondly, we know that there are k known valuation functions or types of agents. So an agent comes in, she's going to have one of these k valuations. Okay, so the valuations, k different valuations are known to us beforehand. And agent will arrive online and she reveals her type. Okay, this is the model. Any questions about the model? Is it clear?
Is it the same as they will randomly arrive and I don't know in what order they will arrive?
I will tell the exact thing. The information structure is this, known beforehand.
Do you know the number of agents of each type?
No. So the online K-type FD as defined has just this information structure, nothing else.
K is not n.
Yeah, K is not n. K can actually be more than n, much more than n also.
It can't be arbitrarily large. Like I can just.
It can be, the model can have it arbitrarily large.
But you can sort of capture the bad example you gave with every possible set is.
You could. So I'm not claiming positive result in online K-type FD. I'll give the result.
My question is related to his, like, if you have smaller k, would you expect to get positive, in particular k equal to 1?
Yeah.
What, I mean, because I have no sense, like, would you get positive results?
If you have k is equal to 1, which means you have only one type, which means all arriving agents have the same valuation function, you can just solve an offline problem.
Right.
So yes, you would get a better result.
Do you know the aggregate distribution? So I know there is one this type and one that type. So if I know this guy has come, I know the next guy is going to be that.
Yeah, so if we go to the next slide, that will answer these questions. So this is the online K-type FD model, and our results are in two different settings. One is adversarial and one is stochastic. And the adversarial setting is precisely that we don't know anything about anything further. There is an adaptive adversary who will see that, okay, you have seen these many times, let me give the next type of agent. She determines the next type. And then there is the stochastic arrival, where the next type of agent is coming from some distribution underlying.
The same every time.
Yes, same distribution, yes.
And in the first case, the adversary may decide to keep the same valuation.
Yes, adversary can decide whatever she wants. Yes, yes. And it's an adaptive adversary.
At least intuitively, can you say something? As k grows, the hardness also.
We can say it formally. Our result is that we get a computational result that we have a 1 over k approximation in the adversarial online setting, which is actually not so great. I mean, you're still 1 over k away. Unfortunately, we also give a computational lower bound over there for adversarial, which is not surprising, as was pointed out, that if I can keep k to be very, very large and we would get nothing. So
In the stochastic thing, it's prior free, or do you know the distribution?
you know the distribution, but you can learn the distributions, but I'll go with you know the distribution.
Is the lower bound computational or information?
Information. But for stochastic arrival, we do get a very strong positive result that we can get as close to half as possible. Okay. So first, I will talk about the why is it hard over here in this adversarial setting. Okay. I'll give some intuition about why it is hard, and then I'll go to the second result quickly. Okay. So this computational result, as informally we can think, if k is very, very large, then we should not be able to get anything. But what this is saying that even when k is small, you will still not get better than 1 over root k. And this is actually true for binary valuations, not even for general additive valuations. So before I go into that hardness, let me take a step back and tell what happens in binary valuations offline case. Where it exists, it's really very easy. Okay. So consider any instance with n agents and m goods, and I'll give a quick idea of existence of binary online MMS valuations. Okay. So over here on the right side, I have an example running where we have 4 agents and there is 15 goods, and this is, I'll show the MMS allocation of one agent as the algorithm proceeds. So let's say the green goods are the goods that this agent likes. Okay, some agent I likes. So first of all, she creates her MMS allocation. MMS of this agent is 2. Okay, she will try to divide it as much as possible so that she maximizes the minimum value. So the MMS comes out to be 2 for this agent. Now what the algorithm does is it arranges all the agents in order from 1 to n so that the least MMS valued agent is at the first and the largest MMS valued agent is at the last. And the algorithm just gives any mu I goods to the first agent. Why this works is because suppose the first agent in this example, for instance, had mu1 as 2. Okay, so you allocate any 2 goods. So suppose you allocate this red good over here and the red good over here. Then these go out of the system, and the new instance has one lesser agent and the remaining goods. So these can always be arranged because you took away fewer goods than the MMS value. They can always be rearranged into a new allocation where the value MMS remains at least same. So it's nice and easy. They will trivially exist for offline binary valuations in the offline setting. Okay. Even if you don't understand the proof completely, just know that when the situation is offline, it is nice and easy. And the key reason it's nice and easy is because we can order these agents from 1 to n. Okay. In online setting, it does not remain so. For instance, consider an instance where I give you 7 types and only 2 agents are going to arrive online. Okay, so there are only 4 goods. The first type likes all of these goods and the MMS value is 2 for this agent. And the next 6 types like 2 goods each, and the 6 types are just 4 choose 2 goods. Okay, they can like any of the 2 goods. Suppose I want to give this agent full MMS value, the first agent. I give away any 2 goods, then my adversary will just pick that particular type and say that the next agent is of that type. So MMS allocations will not exist in online binary setting precisely because we cannot order them. The large MMS value agent might come in before and just eat up the goods that next agent likes. Okay, so this instance can be extended and gives us the information theoretic lower bound that you cannot get more than 1 over root k approximation. Any questions? Okay. So these were the contributions. I told a little bit about this 1 over root k non-excess hardness. I will spend most of the rest of this talk telling about how we get this positive result over here.
You can extend it to even random order arrival, right? Like
Yes, the hardness will extend to random order arrival. I think we had that, but yeah, we know.
One guy has to be like this 2, which eventually will show up later down the road.
And will show up like somewhere in the middle with high probability. I think so, but we had something, but I don't remember exactly, but I think it should be possible.
Then doesn't the lower bound extend to stochastic arrival?
No, random order is an adversary picks the agents and then just sends them in random order.
Okay.
Stochastic arrival is there is a distribution in which the agents are coming, from which the agents are chosen.
Random order is like harder.
Yeah, which is what I'm saying. Like even for random order, you have a lower bound.
Yeah. Okay.
So random order is harder than stochastic.
The secretary model.
Okay, and even this result is under some distributional assumptions. So it's not like complete random order we could know.
Is the half in expectation or?
No, it's ex post. Half for every agent. Okay, so this stochastic arrival, precisely it's this, that the agent is of type T with probability Pt. Okay, the distribution is fixed and this is the distribution known to us beforehand. So our main result is that in an online K-type FD instance in the stochastic arrival model, under some distributional assumptions, we get an arbitrarily close to half approximation with high probability. So the high probability is very high probability. It is 1 minus e to the order n. Okay. So the technical conditions are that the least probability over here, Pt, has a lower bound of k over root n. So this inherently bounds the number of types. That is why this makes it easy. Okay, this is the intuition for why the lower bound benefits us. Okay, and so the exact result that we get is when the minimum probability is bounded by k over root n, we get for a large enough n, we get a 1 over 2, 1 plus eta. So to interpret this result, it is like you give me an eta, which determines your approximation factor, and you give me the k, which is the number of types you know are in your system, and I'll give you an n for which the result will hold. Okay, for which the approximation will hold. Okay, so like it was pointed out, Vignesh pointed out, I want to just note that the guarantee is not an expectation, it is an ex post guarantee for all agents. So everyone does get half MMS in the online setting.
Ex ante is much easier.
Ex ante is much easier. I could just give 1 over n with that is just MMS and yeah.
Sorry, what is ex ante and ex post?
Ex ante is just in expectation they get this value. So if I give to each agent a good with probability 1 over n, like independently randomly sample a good with probability 1 over n, upfront I decide this allocation, then this allocation is just going to be x ante MMS allocation. It's actually x ante proportional. Everyone gets 1 over n of their total value, which is more than the MMS value, because MMS is a discrete version of this proportionality.
So one can also think about best of both worlds here?
Yes, that would be a nice, yes. Okay, so the intuition for the positive result is, what would the first, so we have this distributional, we know something about the distribution, so we have to use it, right? So what is the obvious approach? You know that agents of type T arrive with probability Pt, so we create n Pt agents for type T, okay, and we just solve an offline problem, offline MMS problem, and then fix the allocation over there. This is of course not going to work. It will not guarantee any ex post MMS value for all, because there is variance. So if I say there are npt agents of type T, there is a very high probability that there are npt plus 1 plus 2 plus actually up to root npt agents of type T that will come. Okay, so this would not work. The obvious solution to this is that you accommodate this variance into your offline problem. You say that, okay, let me solve this offline problem with a larger number of agents, which allows for this variance within the system. So instead of npt agents, I'll create 2 npt agents. And if I could actually solve an offline problem with 2 times npt agents of type T, I would be golden. That is a high probability result.
But the MMS value...
Thank you. Yes. MMS is very sensitive to the number of agents that are arriving in the system. So for instance, when we have n agents and n goods exactly, you add even one single agent, the MMS will go to 0. Because now you are creating an MMS allocation with n plus 1 agents, and there is no way to make the minimum valued for any allocation is 0. So the max min is going to be 0. Okay, so an offline MMS with larger number of agents has no bearing to an online MMS with a fewer number of agents. Okay, so this will not work. But not all is lost, because when the goods are not actually large value, MMS is very robust to the number of agents in the system. So I will not go into the proof of this, but just trust me on this. If the goods were, suppose MMS is 1 and each good was of value 1/4, I would actually be able to create 2n bundles of half MMS value and then solve an offline problem. Okay, so this basic observation we will build into an algorithm later. Okay, so these are the observations that we have, that when you have MMS is not always robust. We want to solve this problem with large number of agents. It's not always robust, but it is sometimes robust. So we take our system, we move into a robust system, and we solve this small problem. That is the basic idea. Okay, so the building blocks are offline.
Why you have not used this standard ordering reductions? Just that.
We can't use ordering reductions, because ordering reductions will only, once you reduce to an ordered instance, you have to reallocate later at the end. Those reallocations are not, allocations are irrevocable. So we can't use any ordering. So yeah, so the building blocks for this is that offline I'll create. So I create an allocation for, so this T1, T2, Tk minus 1 are the different types. I'm going to create tentative allocations for them in the offline setting. Ideally, like I just said, we want to create 2 npt. So we want to create a little less than this, okay? We want to create just enough to allow for the variance. But for simplicity, let's say we create 2 npt, exclusive bundles for each type, okay? We saw that because when high valued goods are present, we can't do this. When the goods are only low valued, we can actually do this. When the goods are high valued, we cannot do this. So what we'll do instead is we'll create overlapping tentative allocations for the agents. So there will be some bundles that go in every agent's tentative, every type's tentative allocation. Okay, we won't keep these bundles exclusive. So there are 2 factors at play here. One is these overlapping bundles. When we have overlapping bundles, what we do is we can create more bundles in the offline phase, and they can just be allocated. So there are more possible tentative allocations available for each type. The bad thing about the overlapping bundles is that in the online phase, if I remove a bundle from someone's type and it was overlapping with someone else, that agent's bundle is also gone because it's no longer available. Someone else took it. Okay, so the depletion is faster for overlapping bundles. And we have exclusive bundles. Exclusive bundles are good in the online phase because only the type who has arrived takes this bundle. But in the offline phase, they take away the value from other agents. So they don't allow us to create more bundles. So these two factors play with each other. And what we want to do is basically answer the question of how many overlapping and how many exclusive bundles to create so that we can maintain this high probability guarantee in the online phase. Okay, so this gives us a three-phased algorithm where phase 1 we allocate what I will call as the universally high valued goods. Phase 2 I'll create bundles, tentative allocations of high valued goods, and phase 3 I allocate the small valued goods. So phase 3 is easy. Phase 3 is just easy. Small valued goods are easy, as was discussed beforehand. Universally high valued goods are okay. So I draw, I show how these phases work at a very high level in the next slides. So on the right, I have these tentative allocations, and I'll show how the algorithm creates them. Okay. So for phase 1, which is allocating universally high valued goods, which are basically goods that are of large value for all of the types. Everyone agrees that this is a very nice good to have. Okay. So we separate out these high valued goods. I don't know if the colors are visible, but I'm coloring some of the goods over here. These are the universally high valued goods. These goods are given as overlapping bundles for all types. They exist as tentative allocations in all types. Okay, they are completely overlapping. Then for phase 2, I want to allocate the high valued goods. Okay, now the high valued goods are the goods that are of high value for some, but not all agents. Those are the universally high valued goods which we have already tentatively allocated. So for these, so suppose NH was the number of, so the intuition behind how to allocate these goods is that if NH was the number of universally high valued goods, then when NH of the agents come in, they can be of any type, I can just allocate one of these goods to them. Okay, so it doesn't matter which type they are. So for the remaining agents, which is N minus NH, I will do this variance game. That I will say that, okay, I'm going to create 2 n prime PT agents for exclusive bundles for each of the remaining types. Okay, so I'll define this notation where saturated types will be, so I define ET to be this 2 n prime PT, which is the number of bundles that I want to create for type T. Okay, and saturated types are those types for which I have created these bundles, and unsaturated types are those for which I have not created these bundles yet. So EP is the number of exclusive bundles kept for type T. Okay, and that is number of overlapping bundles is NH, N minus NH is N prime, and 2 N prime PT is the number of exclusive bundles I want to create. Okay, and I will just give a quick intuition for why we can create them in the next slide, but are there any questions here? Because I said at the beginning that we cannot create 2 NPT bundles. MMS is not robust to number of agents. Now I'm saying that I'll create these many bundles that are overlapping, and now I can suddenly create 2 N prime PT bundles. Okay. Okay, so why can we do this? We do it algorithmically. So these are the tentative allocations we have already created over here, okay, the universally high valued goods. Now what we do is we look at the high valued goods, okay, all goods that are high valued by even one of the types, okay, and we separate them. So S1 to Sk are the sets. S1 is the set of high valued goods for type 1, Si is the set of high valued goods for type 1, okay. I create this, I separate these goods out, and then I will arrange the types in order from 1 to k in one of two possible ways. Either these two sets, there are two sets, Si and Sj, so that there is very little overlap between them. Okay, if there exists two sets such that there is very small overlap of goods, the intersection is small, then those are my first and last agents. If there is no such two sets, then I just order the first, the highest probability is at first and the least probability is at the last. Okay, in one of these two ways, we'll order the types. And then the algorithm is actually very simple to allocate the goods. For each type, we remove from its own high valued set up to ET bundles and allocate them exclusively. The reason...
So in case 1, you don't care about the middle?
No, it's the first and last that we care about. Okay, the intermediate, okay, yeah. we can arrange the intermediate agents in any way. It's the first. So because there is always a last agent who is not taking away goods from any of the agents. The first up to k minus 1 types are very happy. It's okay to allocate to them. It's the last type that gets killed by the first. So when we are allocating exclusive bundles, the basic thing is no other type should be taking away too much of your value. For all the first k minus 1 types, the last type is there, not taking away too much value. So we can guarantee a good enough value for them. For the last type, we cannot guarantee that. So that is why we only need to care about the first and last type. Okay. So the key idea for why this works is, like I already said, early types will not lose any value to the last types. So it's okay, the first k minus 1 types are fine in this. And if the overlap between the first and last is small, then the last type is not losing much to the first type, again. So they don't lose much. And if there is a large overlap of all types with respect to each other, then we have already separated the universally high valued goods. So we can bound, using pigeonhole-like argument, the total number of these high valued goods itself. So no one is losing much in this phase at all. And this overall says that we don't lose too much value over here. This is a very high level intuition, but yeah, I hope this was clear enough.
Can you repeat what you do with the very high value object?
Very high valued, universally high valued ones that are liked by everybody, they are just allocated to all of the types in overlapping bundles. So you can think of it this way, that if there are some very high value, if there are some goods that are universally high valued, everyone likes them, then I can think of it as a reduction to a smaller problem. The first NH agents who are going to come, I'm just going to allocate them. My MMS is nothing is changing in my problem. The reason we don't do exactly that is because NH might be too large, which will make the second thing too small, and then we won't get statistical guarantees on the other one. So we can't reduce it exactly, but the reduction is the basic idea of why they are.
So you assign them and then do you clear ties arbitrarily? What is it? So if you overlap the goods, so when you're finally assigning the goods, what do you do?
We allocate the overlapping. So there are two different phases of the algorithm, depending on. Okay, you can just think of when an agent of some type arrives, you will allocate any bundle from its tentative allocation. If it exists in other types, you delete it from those types. Okay.
Yeah.
Okay. Okay, so the overview is the universally high valued goods are allocated in overlapping bundles to all types. The high valued goods are allocated by the algorithm I just explained. These are exclusive singleton allocations, and we bound loss by bounding either the number of goods lost, basically bounding the number of goods lost to other agents. Okay, and phase 3 is the small valued goods, which I did not go into, but bag, for those who are familiar with MMS, a bag filling argument just works for them to create enough bundles over there. Okay, so that just a bag filling argument. So basically, like I said before, for exclusive allocations, we need to bound the loss to other types. When the goods are small valued, it is easy to bound this loss. When the goods are high valued, we give this algorithm where it is the loss can be bounded. And other overlapping allocations, they're just overlapping, so there's no loss over there. Okay, and then we get this result for. So one of the other reasons why we have this probability of types, basically, now that we have seen the algorithm, is that this last type has a large enough probability that there is not too much loss to the first k-1 types when we are allocating the high valued goods. Okay, so we have some other results where our first result is that we can extend this result to this probabilities not being known upfront. The algorithm can learn these probabilities from the first few agents, so using a sublinear number of agents. So basically what we do is we divide the goods into two parts. In the first part, we run the adversarial algorithm with a very large, and we lose a lot in the first part of the algorithm, but we lose it to a small number of agents. And using the adversarial algorithm, we allocate those goods to those agents. We learn the probability using in the first phase, and in the second phase, we use the stochastic with known distributions, and we allocate them with a constant probability. We can also handle noisy valuations in a pretty straightforward way. If the valuation functions are some constant beta factor away, then the MMS guarantee loss is beta squared. This is quite standard. But this is also there. Future directions are other fairness notion. So we have a model where we can give tractable results for online problems. So looking at other fairness notions in this model, closing the gap for adversarial setting, we have a positive 1 over k and negative 1 over root k. So that gap is still open. Improving the approximation for stochastic setting, I don't think half is the right answer in the stochastic setting even. We can probably improve it. And relaxing the distributional assumptions of this lowest agent, even for special classes of valuations. Those would be good directions. Other future direction is the model itself. Right now, the online KFFD model has number of agents, k-known valuation functions type, and agent arrives online and reveals it. So how do we, in practice, how would we find out these valuation function types? AI-based predictions, okay? And for instance, if you look at Amazon, they have these warehouses set up, and they do have on their website listed that they have analyzed the data of the kind of products that will be needed by people. Similarly, Google uses flood forecasting to determine how many people and who will need goods, what kind of goods will be needed. FEMA, which is a Federal Emergency Assistance Agency in the US, or at least it was until the government changed. They also use AI-based predictions to determine who will need what kind of help. So the predictions of the known valuation functions, we are not so far, like assuming this in our model, it's not so far from what happens in the real world scenarios. What a good next step for this model to actually be useful in the real world would be a noisy prediction of n. Knowing n exactly is not a very realistic assumption. So a noisy prediction of n, where n is predicted between a constant factor, that would be a good future direction. And of course, valuation functions make it more free. We have these exact k valuation functions, but instead of that, they are drawn from a distribution. Okay, that's it for me. This is summary of results. Thank you for listening.
There's a model which is like augmented supply that you can get very good MMS guarantees if you allow some addition. So you compute MMS.
Some copies of goods, right? Yeah, I've seen. Yeah.
So is that interesting here? So I don't have the agents say I go at this running example, like you do fall short on water or some other, so you are able to replenish it. So it's just that the MMS is computed with an initial set of goods. But if required, to a bounded extent, you can add certain copies of certain things. The point would be to quantify
how many goods to add.
How many copies you need, and there are nice results. With n minus 1 copy, you can get exact MMS.
Yeah, I've seen them. Maybe, I'm not sure, because it gets away from this problem of n agents and goods and. But I honestly, my instinct would be I don't think so, because the basic problem that an agent comes in, I give her some goods, and the future valuations I don't know of other agents. This can be true for any agent, right?
I assume k types, but what I'm saying is, okay, let me rephrase. Say there are no very high valued goods. I give you an instance here.
Yes, if there are no high valued goods
at all,
then it's a very simple problem. Yes, it would become very simple. So you are saying that you will create copies of these up to 2n. Yeah. Okay, yeah, that would make sense. Yeah, I think that would give like strong positive results though.
So, first of all, thank you, very nice talking. The lower bound you had for the adversarial setting was binary.
Yes.
Do you have a better upper bound for binary itself?
Yes, we have a matching upper bound for binary. I think so. Close to matching.
In the adversarial, I mean, the positive result is much better.
So we have a matching lower and upper bound in the binary setting, and I have forgotten what exactly that bound is, but it's I think mu min over mu max is the approximation that you can give. So the algorithm is trivial. You give the lowest thing, and that is the best you can do. So it doesn't depend on this k. but we have matching upper lower bounds for binary setting.
I think I missed this, but like what happens? How crucial is that assumption that minimum property of types is bounded by this omega of k?
It's very important. We don't get results otherwise. But it would be good to extend it to unknown.
Let's thank
Thank
speaker
you.
again.
Thank you so much.
The mic.
Oh yeah, the mic is here. Hey. So, do you know where your talk is over here?
No. But I did mail to Shiva.
Should be here. So this is. Yeah. Okay, so next we'll welcome Dr. Nidhi Rathi. Nidhi is going to join the University of Warsaw soon as an assistant professor. She was a Lisa Meitner postdoctoral fellow at the Max Planck Institute of Informatics. Her research spans algorithmic game theory, fair division, and computational social choice, with a strong focus on the math and algorithmic foundations of fairness. She completed her PhD here at IISc in the Department of Computer Science and Department of Mathematics, and her work received departmental commendation and an IBM PhD fellowship. Today she will talk about achieving maximum share and envy freeness guarantees simultaneously. So let's welcome her.
Thank you for the invitation. So today, as Rito said, I'll be talking about achieving two distinct kind of fairness guarantees, maximum share and envy-based guarantees simultaneously. And I'll explain everything as we go along. This is a joint work with Hannah, who is in the audience and whom we have already listened to. Okay, so let's start. So the setup, the problem that I'm talking about today is this fair division and resource allocation setting. And here there are fundamentally two questions that we study. The first is, what is fairness as a concept? And this has historically been studied by economists, political scientists, and mathematicians. And then at the turn of century, as mentioned previously, another question started to be studied, which is how to compute a fair allocation. And so the setup is, we have these agents with valuations over a set of items or goods, discrete sets, discrete items, and the overarching goal is to find a fair allocation of these items among the agents quickly. Okay, so let us see the notations. We will use set n to denote the set 1 to n of n agents, and the notation I'll be using is ijk. We have a set m of m items, and I'll denote them using g1, g2, and so on. There's a valuation function which specify the preference function of every agent over the set of items, and will be represented by vi. And in particular, vi of s simply tells you how much agent I value the bundle s of items. And throughout this talk, I will assume additivity of valuations, which simply means that value of any bundle is nothing but summation of the values of its constituent elements. And an allocation is a partition. I'll denote using A's, so A1, A2, AN, and n partition of items into n bundles or n sets. And here, bundle AI will denote the bundle that I've assigned or allocated to agent I. Okay, and as I've mentioned, the overarching goal is to divide the given set of items among n agents in a fair manner. Okay, so let us try to understand what is fairness as a concept. Largely, there are two different kinds of fairness concepts. One is comparative, and another is in absolute terms or threshold-based guarantees. And in comparative, what you do is to evaluate an allocation as fair. Each agent compares her own bundle to other bundles in the allocation. And the quintessential guarantee here, or the fairness notion here, is that of envy freeness, which simply says that an allocation would be envy free if there's no envy, in the sense that every agent thinks that whatever bundle she has been assigned to, she values that bundle at least as high as whatever she values any other bundle in the allocation. And in absolute terms, here what we do is each agent defines her threshold value based on her view, and her view is her valuation preferences. And she says an allocation is fair if she gets a bundle that has value at least as high as this threshold that she is defined. And the standard notion here is that of proportionality, a very natural notion, which simply says that every agent must receive a proportional share. Okay, but as we know that in divisible setting, when we have a cake modeled as a 0-1 line segment, these problems become very simple, at least existentially. We know that envy-free allocations and hence proportional allocations exist, and they come from beautiful fixed point arguments. But as we move to discrete setting, which is the focus of today, we know that envy freeness and proportional allocations may not exist, and hence we need to understand what are the right notions of fairness in this discrete setup. So when we relax fairness, what we do, the first relaxation is that of envy freeness up to one good. So here, what we need is, sure, there may be envy in the allocation, but the envy must vanish as soon as I remove some good from that other envious bundle. And we know that this always exists and can be computed in polynomial time. And another stronger relaxation of envy freeness is that of envy freeness up to any good, EFX. And here the envy must vanish away when you remove any good from the other envious bundle. So Vi of AI, this value must be at least as high as Vi of Aj minus any item in that any item G in that other bundle Aj. And the major open problem in this setup is to understand whether EFX allocations exist or not. And there are several approximations, several work, relaxations that has been extensively studied. And now, when we relax proportionality, which Pooja has been talking about, is this maximum share based guarantees is that we study. And here, each agent's threshold is equal to the best guarantee that she can achieve when dividing items into n bundles and receiving the least valuable bundle over there. And this value, this threshold value, is defined mathematically as mu I, which is maximizing over all allocations B and then getting the minimum valued bundle in that allocation, which is minimizing over J in the bundle set Vi of Bj. But so this is this MMS guarantee. And here what we know is, we know that MMS allocations may not exist always. And we know that MMS implies EF1 plus PO guarantees. And for approximation guarantees, which again we have seen a long list of relaxations and approximation being studied, we had petas for 3/4 plus epsilon MMS guarantee. And now recently we now have a better guarantee, which is F petas for 7/9 minus epsilon MMS. Okay, so this is like these two interpretations of fairness that we study in this line of work. And the focus of this work and today's talk is to understand what can we do when we want these different kinds of notions to exist simultaneously. So these notions of envy-based EF1 and EFX and MMS, they capture different aspects of fairness. And intuitively, to understand this, the reason is because either of EF1 and EFX or MMS properties, they do not necessarily imply particularly strong approximation guarantees for the other. And hence, they do represent different aspects of fairness. And the focus of today's talk is to understand how to attain good approximations, good guarantees with respect to envy-based and share-based notions of fairness simultaneously. Okay. Any questions for the setup for the problem? Okay. So our results, the main result that I'll be talking about today is that we prove that there exists a partial EFX plus 2/3 MMS allocation. So note that partial is important because we don't know the existence of EFX, complete EFX allocations. And before that, the best known approximation guarantee known was partial EFX plus half MMS, and we improved this guarantee of half MMS to 2/3 MMS allocation. And other incomparable guarantee which was known was complete allocation, but 0.618 EFX plus 0.553 MMS approximation guarantee. So this is the first result that we have, and we'll discuss the proof for this result. And the next one is, given this partial allocation, I can make it a complete allocation, and I will achieve a complete EF1 plus 2/3 MMS allocation. And again here, the best known guarantee was EF1 plus 4/7 MMS allocation, and we improved the 4/7 approximation to 2/3. And moreover, there exist a p-TAs to get arbitrarily close to these approximation guarantees. Okay. So now I'll give a brief overview of our techniques. So the starting point is the 2/3 MMS algorithm. So we start with this algorithm, and we understand what is lacking in this algorithm and why it is incompatible to achieve any NV-based guarantee simultaneously, and what can we do to have NV-based guarantees simultaneously. So I will go over this algorithm quickly. What this algorithm does is, it's an iterative algorithm, and it removes agents one by one and move towards smaller instances iteratively. And how does it do is, like, while the set of agents in the system is non-empty, that is, not all agents have received a bundle, what you do is you simply pick an arbitrary agent, and then you ask that agent, okay, with the remaining set of items, you give me, let's say n is the number of remaining agents, you give me an n partition of the remaining items, so that all bundles are 2/3 MMS bundles for you. And we know that we can do that because it's basically an identical valuation setting, and we can achieve 2/3 MMS there. Okay, now what we do is we create a bipartite graph. So we'll have agents on one end, which is like in the figure you can see it there at the bottom. We have 1, 2, 3, this all agents. Let's say we are in the beginning of the round. We have n agents, and we ask, let's say arbitrarily, we ask agent 1 to give me an n partition of all the items, so that every bundle, this A1, A2, A3, AN, is 2/3 MMS bundle for agent 1. So she does that, and now what we ask is, every other agent we ask, okay, now you draw an edge to all the bundles you find 2/3 MMS. That's all. So we say that there are these desirable bundles for them, because till now we just want 2/3 MMS. So they draw this edge of desirability to all the bundles, from which they can incur 2/3 MMS guarantee. And now note that if there's a perfect matching already in this bipartite graph, I am done, because every agent will be assigned a bundle from her, so that she achieves a 2/3 MMS value. But if not, what you can think is, there will exist a Hall's violator set, because there's no perfect matching. So there are two ways of looking at this Hall's violator. One way, or one natural way, is to understand, okay, there is a set of agents, a subset of agents whose neighborhood set is set has a cardinality of strictly lower size, which means that, let's say there are these 1, 2, 3 agents. Forget the figure right now. There are, let's say, a subset 1, 2, 3 of agents who only like, let's say, bundle A1 and A2, which means like the allocation, the partition I've done is so that I cannot satisfy all these 3 agents simultaneously. They only find 2 bundles desirable. And the other way of looking at this is just reverse the thing and look from the side of bundles. So, which is what is shown in the picture here. What you can think is, let's say there is a Hall's violator, right? There's no perfect matching right now. So let's say there is this Hall's violator A1, A2, A3, this set S. The set S is a subset of bundles now, which are desirable to only a set of agents which has a strictly lower size. So in this example, these A1, A2, A3 only satisfy agent 1 and 2. So these bundles are not good enough for good enough number of agents, and hence you will not be able to find a perfect matching. And now if I take a minimal Halls-Violator set S, which is a subset of the bundles, what I can do is I can find a matching that covers the neighborhood at every agent in the neighborhood of this set S. And why I can do it? Because this is a minimal Halls-Violator. Any removal of a bundle in this minimal Halls-Violator, I know that there's a perfect matching because it's a minimal Halls-Violator. And hence I can find a matching, a good matching, that will cover every agent in the neighborhood set of this Halls-Violator set S. And that's what I do. So so this is the dark edges. Agent 1 is mapped to bundle 1 and agent 2 is mapped to bundle 2. You do this. So you allocate bundle A1 to agent 1, bundle A2 to agent 2, and they are removed from the system. Now what you have is a smaller instance of n minus 2 agents, 3 to n, and the union of all the remaining items, A3 union A4 till AN. Now note that these remaining agents, agent 3 to n, they did not find any matched bundle desirable, right? Because they were not in the neighborhood set of S. And which means that these bundles were of value less than 2/3 for them, and and we can show that if that is the case, they have enough value left in the remaining sets. And 2/3 is basically a tight bound which you can get from this kind of analysis. And hence, all the remaining agents are still happy. They'll still be able to do the same thing iteratively. Like now you can ask agent 3, let's say without loss of generality, to now give me an n minus 2 partition so that every bundle is 2/3 MMS for you, and so on and on. So at the end, what you'll have is a matching or an allocation where every agent will be assigned a bundle that gives a 2/3 MMS guarantee, and that's it. So you get a 2/3 MMS algorithm and allocation. So okay, why does this algorithm makes progress? One is the neighborhood set of the Halls-Violator is non-empty, because note that agent 1 in this figure, she has drawn edges to every bundle. So which means neighborhood set of any Halls-Violator you assume would be non-empty, and hence at every iteration at least one agent will be assigned some bundle and she'll be removed from the system. And the second point I've already told, that after removing the matched bundles, the remaining agents still have good enough value left in the remaining items. But yeah.
Where is the number 2/3 coming from?
Yeah. So this particular thing, that you have enough value remaining in the set of items. This, if you just optimize, 2/3 is the bound you get. Like if you remove less than 2/3 value bundles, you'll have enough value remain, 2/3 MMS value remaining in the remaining set of items. Okay. Yeah. But now note that the problem with this algorithm is, here as soon as an agent receives a bundle, she's taken out of consideration, and we never look at her bundle ever again in the future. This particular feature of the algorithm is now incompatible with achieving any NV based guarantees, because what can happen is agent 1, even though she got a 2/3 MMS bundle, she may have strong NV or even EF1 NV to any, let's say, agent 3 in the future, because she may like that bundle much more than whatever she've gotten, even though she've gotten 2/3 MMS guarantee. So this particular feature, because we are not taking a look at it in the future, we cannot achieve any NV based guarantees with this algorithm. And why is it incompatible? In particular, there are two problems. What can happen is there will be strong NV from agent I to J if they are removed at the same time. This is possible. Even though agent 1 got it, but agent 1 can still strong NV bundle A2. And the other possible source of strong NV is there will be strong NV from agent I to agent J if I is removed before J. This is what I explained. Okay, so what we do is, we start with this particular algorithm and we modify it to show that we can still maintain 2/3 MMS, but on top of it we can get EFX, but with partial allocation. So what do? We remove this myopic nature of this 2/3 MMS algorithm by looking into the future and modifying the already allocated bundles. And interestingly enough, you'll see that the share-based guarantee, this 2/3 MMS guarantee, that we maintain for a subset of agents, that is whose size keep growing, will help us to prove NV based guarantees as well. Okay, so what are we doing? Fix 1 is in each step what you do is you shrink the bundles as much as possible such that each bundle still has a neighbor. So note that agent 1 made these bundles A1 to AN, but don't be happy with these bundles at all. What you do is you shrink these bundles even more as much as possible such that each bundle still has a neighbor, and that's all I need for progress to be made. But what will this ensure is there will be no strong NV from agent I to J if they are removed at the same time. Okay, let's try to understand why will this hold true, because again look at agent 1 and 2. If agent 1 strongly envy agent 2, it simply means that agent 2 should have had the shrinking process happened, because even after shrinking of A2, A2 will have a neighbor which would be agent 1. So therefore, if you're shrinking the bundles as much as possible, such that each bundle still has a neighbor, there will be no strong envy among the agents who are allocated a bundle in the same iteration, same step.
So, but this still doesn't give any guarantees of what bundles.
Still doesn't give any guarantee?
In the future.
Yeah, that's the next thing. So this kind of neighbors I and J are taken care of, who are matched at the same iteration. And the next thing what you do is, if a removed agent, so now look at agent 1 and consider some future iteration. So if a removed agent, say agent 1, she now strongly envies a matched bundle which is being produced in the next iteration. What you do is you shrink that bundle B as much as possible such that still some removed agent I still envies that bundle. And now what you do is you just give this shrinked bundle B to I, the past agent I, and add whatever was allocated to I again back to the pool of remaining items. And this will ensure that there will be no strong envy from agent I to J if I is removed before J. So what you have simply done is, agent 1 was gone out of this picture, at least into two-third MMS algorithm, but what you do is you take a look at them again. If agent 1 says that, you know what, whatever bundles now you have done in this particular future iteration, I would have strong envy from this bundle, what you do is you shrink that bundle as much as possible such that still some removed agent from the past envies it, and you give that bundle to that agent, and you will maintain two-third MMS because she still get a bundle of at least that much value. She's still getting a bundle of higher value. So you maintain two-third MMS guarantees. And in basically in fix 1, why were you maintaining two-third MMS guarantee there? Because it was still, every time you will always give a bundle to an agent if there was an edge, and the edge always represents two-third MMS guarantee is possible. And that's it. Okay, so now you would think that, okay, what happens about the other way around, that agent 3 may have strong envy to agent 1, like agents from future to the agents to the past. But note that that is not possible, because agent 3, whenever she gets a bundle, she will have a value of at least two-third MMS. And we know that agent 3 did not have an edge to any of the bundles from the past, A1 and A2, which means those bundles were of a value less than two-third anyway. So there will be not even envy from future agents to past agents. And yeah, that's it. So that's how we get EFX plus two-third MMS, but a partial allocation of that.
So this is a sequence of Pareto.
In the sense that whenever we are doing this shrinking, or
you are allocating a person who already has a bundle.
Yeah.
Is shrinking someone else's bundle and exchanging that.
Yes.
And releasing that. That's the termination is via Pareto.
No, the termination is still coming from the fact that at every iteration, you're assigning a bundle to at least one agent, and you're having a smaller instance. Because every bundle still has a neighbor, and hence the neighborhood set of the minimal Hall's violator set will always be non-empty at every iteration. So this is not an iteration for me that when I'm swapping in this fix 2, this is not an iteration, this is just an intermediary step.
Yeah, and why these intermediate step terminates is because
Ah, okay, yes. Yeah, okay, I see, okay, yeah.
And which means you can also guarantee that the charity is not envied. Finally.
Yeah. We will, I'll talk about that. Okay, so this modification to two-third MMS algorithm, we get additional EFX guarantee as well. And now, as we all know, it's easy for going from partial EFX to complete EF1. You simply run the NV cycle elimination, and you obviously maintain two-third MMS guarantee doing this, and you get EF1, a complete allocation. Okay, so to conclude, like what we have is now that we have existence of partial EFX plus two-third MMS allocations and existence of complete EF1 plus two-third MMS allocations. And top of it, like as Vishwa pointed out, what you can also do is running this EFX with charity algorithm from Chaudhary et al.'s paper. What you can do is you can have a partial EFX plus alpha MMS allocation, where alpha is the maximum of two-third and this bound 1 by 2 minus rho by n, where rho is less than n, and rho is the number of items given to charity, such that no one envies a charity. This is like the standard EFX with charity bound. Yes.
Yeah, sorry, can you remind me why Licton deserves 2 by 3 MMS?
Because every agent will always get a better bundle still. Like EF1 is just like you're giving more bundles, more items. You're not taking away. Even when you're resolving NV cycles, the value only goes up. Like from the partial allocation, I'm just running the NV cycle elimination to complete it.
Additionally, you can also say that charity is at most n minus 1.
Yeah. So rho is strictly less than n. Yes. And note that this improves the result of from the same paper of Chaudhary et al., where they proved the same existential guarantee, but for them the alpha MMS was the alpha was 1 by 2 minus rho by n, and for us it's maximum of two-third and 1 minus 2 minus rho by n. And that's it. And a natural future direction is to get a better bound. I believe two-third is not the best bound that we can get. At least can we get EFX plus 3/4 MMS guarantee simultaneously. But yeah, thank you.
Any questions?
Where is the 2 by 3 naturally coming from? It looks like you started with 2 by 3 to begin with, and what go wrong? You start with whatever is the best.
No, but
that will go wrong in our
yeah. There was a way that we could modify this two-third algorithms to be compatible with NV-based guarantees. I don't think so we can do that with 3/4 MMS algorithm. Maybe we can, but we don't know how to do it yet.
So this matching-based algorithm does not do better than 2.
Oh, I see.
That does, and yeah, the others will do.
Okay, so let's thank the speaker again.
So this is nothing known for beyond algorithm.
Yeah.
think this is it. It's control L, right? Okay, thanks.
Okay, so this is our last talk for today. We are pleased to welcome Aniket Murekar, a postdoctoral researcher at Northwestern University, who works at the intersection of algorithms, economics, and machine learning. Aniket completed his PhD in computer science from IISc, where he worked on fair division, incentive-aware mechanisms, and market design. He has also collaborated with industry folks at Google Research and Adobe Research. Today he'll share his recent work on constant factor EFX for chores.
Okay. It's a pleasure being here. Thanks, Siddharth, and all the organizers for having me. It's been a long and wonderful day, so I also want to thank the audience for sticking around. So I want to tell you about some recent work on EFX, but for chores, not goods. So this is based on two recent papers with Jugal Garg and John, who are both at IISc. Okay. So the main takeaways of this talk are as follows. We study the fair allocation of indivisible chores. So as opposed to goods, these are items that give a disutility or a cost to agents receiving them with additive preferences. And we study the fairness notion of NV freeness up to any chore or EFX. Now, because EFX allocations may not exist, we don't know if they exist in general. People also have studied if EFX can be achieved in an approximate sense. So there is this notion of approximate EFX allocations, in specifically multiplicative approximations. So in a lambda EFX allocation, where lambda is a number at least 1, it measures how fair an allocation is, with lambda equals 1 being exactly EFX, and the smaller lambda is, the fairer the allocation is considered. So the main results of these two papers are that there exists a constant factor approximate EFX allocation. In particular, lambda equals 2 is achievable. And in obtaining these results, we also have some technical contributions. The first of which is a general framework for obtaining approximate EFX allocations. And one of the steps in this framework is to design good initial allocations, which I will specify in the course of this talk. And in achieving this good initial allocation, we rely on a definition of competitive equilibrium, which we call earning restricted competitive equilibrium. We define this, we prove that it exists, and use it in our framework for obtaining an approximate EFX allocation. So those are the main results of these two papers. So here's the setup. There is a set of n agents, 1 through n, and there is a set m of m indivisible chores. And allocation is simply an n partition of m. So agent I gets the bundle xi of chores. Dij is the disutility of chore j for agent I. So the disutilities are non-negative. You should think of the disutilities as costs that agent I would incur if he were assigned to do the chore j. So agent I gets a disutility of di of xi from the bundle xi, and we assume in this work that the disutilities are additive. So the disutility to agent I from a set S is the sum of disutilities of chores in that set. Okay. So what is a fair allocation, right? So as Nidhi already motivated, one of the standard central notions of fairness is NV freeness. So an allocation X is NV free if for all pairs of agents I and H, agent I prefers doing his own set of chores as opposed to what some other agent H is assigned. So di of xi is at most di of xh. As you can see from this example, if there are two agents and 5 chores that they equally dislike, the player with the fewer number of chores will always be envied by the other player. So envy free allocations need not exist. So this motivated a natural relaxation of envy freeness to the discrete case, which is EFX. So an allocation X is said to be EFX if for all agents I and H, no matter which chore C you remove from agent I's bundle, after this removal, agent I experiences lesser disutility from the bundle xi minus c than the bundle xh of any other agent. Okay. So notice the difference between the definition of EFX for chores and goods. For goods, to remove NV, you remove a good from the other agent's bundle. For chores, you remove a chore from your own bundle. Okay, so there is this subtle difference in the definitions of EFX for goods and chores. Okay, so in this example, the NV between Alice and Bob disappears if this chore is removed, if this chore is removed, and also if this chore is removed. Okay, whether EFX allocations exist or not is a big open question, and it is not known if EFX allocations exist even for 3 agents for chores. Okay. So because this is considered to be a really hard problem, people have studied structured instances, so where you restrict the instance in one way or the other. So suppose there are only 2 agents, or there are 2 types of chores, which means there are multiple copies of the same 2 chores, or the number of chores m is at most twice the number of agents. For all these structured instances, we know the existence of EFX allocations. Another orthogonal direction to attack this problem is to look at multiplicative approximations. So in a lambda EFX allocation, where lambda is at least 1, you want the disutility, the NV between any 2 pairs of agents, to disappear after the removal of any single chore from agent i's bundle, but up to a factor of lambda. So di of xi minus c should be at most lambda times di of xh for all pairs of agents I and h, and for all chores c that you remove from xi. And then the question naturally is, instead of looking at structured instances where you restrict the specific kind of instance that you work with, you ask what is the lambda for which lambda EFX allocations exist for generic instances, for all instances. So prior to our work, the best known existence result was order n squared EFX allocations, where n is the number of agents. And there were also papers which tried to combine the multiplicative approximation in specific structured instances. For example, 2 EFX allocations were known for 3 agents for bivalued instances where the disutilities of the chores are one of 2 given numbers. Okay, and while all of these works use really clever ideas and sophisticated algorithms, the approximation factor was somewhat unsatisfying. So in particular, constant factor EFX existence was not known. And more generally, some of these results relied on extensive case analysis, real hard work, and heavily used the special structure of the instance. Like really made use of the fact that there are only 3 agents, or there are only 2 types of disutilities and so on. So this also pointed to the need for some new or general techniques. Okay. So our main results, as I have already indicated, are that for the multiplicative approximation of lambda EFX, we know that we show that 2 EFX allocations exist. So in over here, lambda is equal to 2. And this improves the order n squared EFX approximation that was known previously, and also matches the results that were known in special cases like for 3 agents. So questions about the problem and the results? Okay. And one of the main ways in which we do this is we give a general framework for obtaining approximate EFX allocations. So it works as follows. We start with a good initial allocation, and I'll specify precisely what this means. We perform a series of chore swaps. Again, I will specify what exactly this means, until we end up with an approximate EFX allocation. And the good thing about this framework is that it is unifying, because not only are constant factor approximation results fit into this framework, but so do some other results in special cases which used different techniques. Secondly, it is algorithmic. So provided you give me a good initial allocation, there are at most n chore swaps which can be implemented very easily in polynomial time. And in particular, this gives a faster algorithm for EFX when the number of items is at most twice the number of agents. And lastly, as you will see, the framework is quite simple. The result of 2 EFX for 3 agents relied on a really complicated case analysis through this framework, I hope you'll see that it turns out to be really simple. Okay, so let me start by motivating how we arrived at this framework in some sense. So here is this definition of EF1, which is a weaker sort of relaxation than EFX. So in an EF1 allocation, you just want the NV between pairs of agents I and H to disappear after the removal of some chore C from agent I's bundle. Whereas in EFX, you want this NV to disappear after the removal of any chore C from agent I's bundle. So if all chores are somewhat small in a sense that I will define, then it turns out that EF1 actually implies approximate EFX. So if you start with an EF1 allocation, so let's say if X is an EF1 allocation, then di of xi minus c is at most di of xh for some c. If you have this additional property that di of c is at most beta times the disutility to I of all the chores that are left over for some beta, then you can just add up these inequalities and conclude that di of xi is at most 1 plus beta times di of xh. So if you know that chores are small in some sense, in particular if one chore C in agent I's bundle is multiplicatively smaller than the rest of the chores, then EF1 implies a multiplicative approximation to EFX. So using this idea, multiplicative approximation to NV freeness, in fact, exactly. So using this idea and the NV cycle algorithm actually was used to give approximate EFX guarantees in some restricted settings. But this idea doesn't really work in general, because what if there are high disutility chores, right? So here the highest disutility chore C of agent I was nice in the sense that its disutility was bounded by beta times the disutility of the remaining chores. What if this is not the case? So what happens if this is not the case? We try to address such situations using this idea of a chore swap. So suppose there is an agent I in the allocation xi. You identify the chore ji that gives the highest disutility to agent I. So this is the worst chore for agent I. And you bundle all of the other chores together. So green is good, Si is the set of all chores which are not the highest disutility chore for agent I, which is marked in red. Okay. So this agent I in this current allocation X is not lambda EFX for some lambda. So I ends up envying some other agent, let's say L. In particular, let's look at I's favorite bundle, which is the bundle L that I has lowest disutility for. So if I envies this bundle L, how do we fix this? We fix this through a chore swap. And the chore swap works as follows. It transfers the entire bundle XL to agent I and transfers the single high disutility chore to agent L. Okay. So after this IL swap, agent I is left with the set of low disutility chores Si that he previously had, the entire bundle XL that belonged to L, and remember this was I's favorite bundle in the current allocation, and L is left with a singleton chore, the highest disutility chore for agent I. So after this swap, it's clear that L is EFX because L has a single chore. So after the removal of this chore, L doesn't envy anybody. But what about I? Right? So let's try to see if an IL chore swap locally resolves envy. So after this one swap between I and L, is it the case that I's multiplicative envy towards other agents is resolved? So as a first step, let's see if we can even show that I's lambda EFX towards L in X prime. In other words, after this chore swap, in this allocation X prime, agent I has this bundle Si and this bundle XL. Does I lambda EFX envy the singleton chore Ji or not? So in fact, let's be more ambitious and see if we can prove that there is no lambda EF envy. Okay. So can we argue that di of X prime I, the disutility to I for this entire bundle, is lambda times smaller than the di of ji.
And the initial NV was twice, this would get you this.
Yeah, so exactly. So di of xi is di of si plus di of xl, and so there are these two terms here. Si is the bundle of chores that you had, and xl is what you initially got. So suppose si is small compared to ji. So it's not obvious that if the initial NV is twice, then this works out because you still have si. Right. So suppose that si is small compared to ji. So suppose di of si is at most alpha times di of ji for some alpha. Then if you have this assumption, then this is already good for us because you can immediately charge si to ji using this inequality. But you also use the fact that I is not lambda efx before the swap, which means that xl is kind of small compared to xi. And because xi is just si plus ji, this means that xl is small compared to ji. And if you put these two together, you obtain that x prime I is actually small compared to ji. And to make these statements precise and obtain that at the end of it I does not lambda ef nv l, the right choice turns out to be alpha equals lambda minus 1. Okay. So we need to assume that if si is lambda minus 1 times smaller than ji, then after an IL swap, the lambda efx nv between I and L disappears. Okay. So this is saying that if si is lambda minus 1 times smaller compared to ji, if the set of low disutility chores that I had were lambda minus 1 times smaller than the disutility of ji, then after an IL swap, the lambda efx nv between I and L is resolved. So at least if this property holds, after this swap, I and L are both happy. L is happy because L has a singleton bundle, and I is happy because we just argued that it is lambda EF. So what about I is NV towards some other agent H? So here we can use the fact that XL was I's favorite bundle. So di of xi is at most di of xh. Okay, so that's a good starting point. But again, I also has this set of chores si, right, after the swap. So we also require that si is somewhat smaller than xh for every other edge. So what this indicates is that we really require something stronger for these chore swaps to work out, and we require a good initial allocations that satisfies some strong properties. And formally, what we require is an allocation called that we define as lambda EFX friendly. So an allocation X is lambda EFX friendly if we can partition the set n of agents into two sets n0 and nh. The set of agents in n0 are lambda EFX. The set of agents in nh may not be. We want that for all agents I in n0, di of xi is at most lambda times di of xh, xk for all k in n0. So among them, they are lambda nv free. We additionally require that di of xi is at most lambda times di of jh for all h in nh. So remember that ji is the highest disutility chore of agent I. So if you look at the set nh and you collect all their high disutility chores and put them in set h, this is saying that all the bundles here are basically lambda times smaller than all the items here. So it's saying that these set of items are really high in disutility for all agents. And we require similar properties for all agents in nh as well. So the first property that we require is that the set of low disutility items Si for each agent I is lambda minus 1 times the total disutility that I has for any agent in N0, as well as the fact that Si is lambda minus 1 times smaller than the disutility from any chore in H. Again, pointing to the fact that chores in H are really high disutility. So is the definition clear? Okay. So provided we have such an allocation, we can show that if X is a lambda EFX friendly allocation, and suppose there is an agent I who is not lambda EFX, if you perform an IL chore swap on X, then X prime, the resulting allocation, is lambda EFX friendly and I is lambda EFX in X prime. So what this suggests is a natural approach of just repeatedly performing chore swaps, right? Because you start with a lambda EFX friendly allocation, you perform an IL chore swap that fixes NV locally and it remains lambda EFX friendly, so you just repeat this. The problem is that I can redevelop NV after such a chore swap. And the fix to this is that if we perform swaps in a particular order of the agents in NH, then this redevelopment of NV will not occur and we only need to do at most n chore swaps. So let me elaborate on that a little bit. We can show that after the chore swap, agent I has a disutility of at most lambda times the disutility of the singleton chores Ji, right? So this we argued before. Now suppose we perform an IL swap and later we perform an HK swap between agents K, H and K. It may happen that I starts envying K, that is the singleton chore JH. When will this not happen? This will not happen if di of ji is at most di of jh. Because I know that di of x prime I, the bundle that I currently has, is at most lambda times his highest disutility chore ji. If this is at most di of jh, then I won't complain later after subsequent swaps. So that's basically the idea. You reallocate the set of high disutility chores in a round robin order. So what you do is you look at these agents 1 through R in NH, you look at their high disutility chores H, you run a round robin algorithm from 1 to R. In each iteration, ask the agent to pick their favorite remaining chore. So let's say you assign it through J1 prime through J prime R, and then you perform swaps in this order 1 through R. So we can argue that if this happens, there will be no redevelopment of NV. So that's basically the entire algorithm that starts from a lambda EFX friendly allocation Y and outputs a lambda EFX allocation X. You collect the set of high disutility chores, reallocate them through round robin, and in phase 2 you perform chore swaps. So you go from agent 1 to agent R. If an agent I is not lambda EFX, then you perform an IL chore swap and you proceed.
How did you define the high disutility chore?
Okay. This is how I define the high disutility chore. So for each agent I, Ji is the single chore that has highest disutility for I in the bundle Xi. Yeah. And if these strong properties are satisfied, then the overall allocation is considered lambda EFX. But the definition of high disutility is like for agent I.
Yeah. So after a chore swap, there will be an agent with just a single chore.
Yes.
And a lot of agents might strongly envy that agent, but at this point that is okay.
Yes, at that point that is okay, because the next time if someone is really strongly envying that singleton bundle, then we allow that agent to pick up that singleton bundle. That's okay. But I mean, you notice that if an agent gets a singleton bundle and someone else picks that bundle up again, then they will just receive a singleton bundle again. Because in an IL chore swap, the other